Good morning, everyone. My name is Dan Bohush. I'm a researcher in the Adaptive Systems and Interaction Group in Microsoft Research Redmond. And together with my colleague, Sean Andrist, who's also on this call, would like to welcome you this morning to the Platform for Situated Intelligence workshop. I want to start by saying thank you for being here with us for this couple of days. Last check this morning, we had around 460 people registered. We're excited to see all this interest in this workshop, and want to thank you guys. We realize this is a virtual event and sometimes it's a bit difficult with time zones, so we appreciate you being here. I think some of you guys might have already heard or maybe are already using the Platform for Situated Intelligence framework, but perhaps others of you are new to it. Maybe you've just seen interesting announcement that caught your eye and are here to learn more about it. Regardless of the situation, we've put together a great program that will, I think, bring everyone up to speed on the affordances of this framework we've developed at MSR. And so just to get everyone on the same page right from the start, I'll reiterate, Platform for Situated Intelligence is basically an open source framework that provides infrastructure, tools, and components to help develop multimodal integrative AI systems. Now, these are systems that generally leverage multimodal streaming sensory data and integrate many different kinds of AI components together in end-to-end solutions. So at one end of the complexity spectrum, you might have something like a robot that tries to interact with people in an open world setting with coordinated gaze, gesture, and speech. Or you might have a multi-camera setup where you're trying to fuse information from different sensors to understand the collaborative activity or to monitor or help assist during an activity. But it goes all the way down to simpler IoT devices that also process streaming sensory data. The framework has actually quite a broad range of applications and use cases. And our goal with this workshop is basically to get everyone more familiar with it, with the affordances it provides, with the tools that are available. We wanna help answer a lot of the questions you might have. We've left ample times for discussions and pepper Q&A portions throughout the different presentations. And last but definitely not least, since this is an open source project, we want to encourage you guys to get involved and contribute and help us take this to the next level. Now, Sean is going to shortly give us a quick preview of each of the sessions that are coming in the next couple of days. So you'll get a teaser sense of what is coming up. But before we do that, I wanted to make a couple of points just about workshop mechanics. Obviously, this is a virtual event. Again, thank you for being here. We are recording these sessions. I wanted to mention that. And so in case you miss a bit, you will be able to go back and look at it. We will try to post this soon after the event ends. So hopefully you'll be able to go back and look at the various sessions. Also, on the off chance you run into technical difficulties, feel free to reply to the alias that you received the invitation from, which would be, I think, msrevent@microsoft.com. The folks are people that are helping organize this, and the AV folks that are helping us run this and make it smooth will be there to try and help you and with what might be going on. And please be patient with us as we fumble here with slides and screen shares and pre-recorded presentations and so on. Hopefully we'll make it all run smooth. More important point I wanted to make is about questions. We are using Teams Live here because we have a large audience, but we really want this to be an interactive event. We're really looking forward to hear your questions, your thoughts, ideas. So please feel free to use the chat tool at any time during the presentations to ask questions. As I've mentioned before, we've left ample times for Q&A portions during the various tutorials and presentations and demos, but feel free to ask the questions as the sessions are progressing. Sometimes we might answer them directly in chat. Some of them we might discuss them more broadly, at the end of the session. But I would encourage you to use that. We've kept the registration site open, so in case you see these sessions look interesting to you this morning and you feel you have colleagues that might also be interested in it, feel free to point them to the event website And also, it's okay if you want to post about it on social media. Feel free to do that. You can use the hashtag. We've been using PSI open source. The last point I wanted to make with respect to workshop mechanics is that at the end of the event, we'll be sending out a survey. We would really appreciate if you guys can take a couple of minutes to fill that out. It will really help even better understand sort of where the community is, what your needs are, which aspects of the framework are more interesting, and then also coming back to the event itself, how can we better organize events like this in the future? So we'd really love to hear your feedback through this survey as well. And finally, before I pass the baton to Sean to give us a preview of what is coming down in today and tomorrow, I also want to acknowledge and thank the broader SCI community. So you'll see throughout this presentation, Sean and myself and a couple of the other engineers on the Platform for Serial Intelligence development team. But really, this is the work of a broader team of people that have contributed over the years to developing this framework. We've had fantastic collaborators inside MSR and a great support team helping us organize this event. And I want to also thank out, of course, a big thank you to the existing user and contributor community external to MSR, folks that have already started engaging with us on the GitHub open source repo and that have brought very useful feedback and great contributions so far. And we hope to see more of that. And with that, I'll pass it on to Sean, who will give us a teaser preview of the various sessions that we have planned for you guys in the next couple of days.
Hi, everyone. I'm Sean Andrist. I'm a researcher at MSR and part of the SCI team. And the team has put together, I think, a really great slate of content for the workshop today and tomorrow, which will teach you basically everything you need to know about SCI, what it is, what it's good for, and how to use it. So whether you're brand new to SCI or you've already been using it in your own projects, hopefully there'll be a little bit of something for everyone. So today we're going to cover a lot of the basics of the SCI framework and dig into some coding and visualization tutorials. And tomorrow we're going to dive deeper into some special topics, present a few previews of new features we'll be releasing soon. So let me walk you briefly through the agenda so you kind of know what to expect in each session. So first up, we're going to have some opening remarks from Microsoft's Chief Scientific Officer, Eric Horvitz. Then Dan will present a high-level overview of the SCI framework, explaining a bit more about the goals of the framework, what it can do, and outlining the overall architecture of 3 layers. So a runtime with infrastructure for streaming, logging, parallel coordinated computation, tools for debugging and visualization, and an ecosystem of components available in the framework. After that, Dan's going to present a deeper dive into a coding tutorial, showing you how to get started with a first simple application and how programming with SCI really looks like. So in this case, we'll build a very simple first application to do voice activity detection. And in the process, we'll take a brief look at how to visualize the data collected from your application and how to tune your application. Then after a short break, I'll present a complete overview of a central and essential tool in the SCI framework, which we call Platform for Situated Intelligence Studio, or SCI Studio for short. And SCI Studio is a really useful tool for visualizing multimodal data streams persisted by SCI applications, which is really important for debugging and iterative development. I'll also present some recent features of SCI Studio to create custom temporal annotations over your data. And then finally, after a break for lunch, we'll have a live panel discussion on how to build, nurture, and continue to grow an active open source community around SCI. And for that panel, we've invited a few longtime and active users and contributors to the SCI framework from both within MSR and in the wider GitHub and academic research communities to kind of help us drive the conversation with everybody. And then tomorrow, as I said, we'll involve some deeper dives into special topics, including how to interop with various other ecosystems, and we'll preview some new stuff we've been working on. And so after we kick things off, we'll start the day with a presentation from Nick Saw on how to use some of the powerful affordances and tools in the SCI framework for collecting diagnostics information on your SCI pipelines and debugging them. And diagnostics information can be collected and persisted from your live SCI applications and visualized like you see here, where you can kind of see all of the individual components, all of the various streams connecting those components, drill down into different levels of detail. and query different kinds of diagnostics information about message throughputs, latencies, and so on. And this is super helpful for debugging issues as your applications grow in scale and complexity. And Nick is going to walk you through a few different kind of common debugging scenarios. In the next session, Ashley Finello will present an overview on interoperating between Psi and other programming languages in general, but particularly focusing on Python. So he'll describe our cross-process messaging infrastructure and do a coding session from scratch, bridging media capture in Psi with face detection in Python. So along the way, he'll explain a bit more about the importance of timing information in Psi and some of the stream synchronization capabilities. Then after a quick break, Ashley will be back to talk about another interop scenario, interoperability with ROS. So some of you are probably familiar with ROS, which stands for Robot Operating System. It's very popular in the robotics community. And in this session, we'll talk about how you can construct hybrid systems that leverage both Psi and ROS. So Ashley will again go through a full coding example, showing how to connect the ROS turtle sim with a simple Psi application that will be used to drive the virtual turtle around. Following that, Dan will preview an upcoming feature on interoperating with the HoloLens 2 device. So as you might know, this is a mixed reality headset that includes a large number of sensors and produces many multimodal data streams. So Psi is really a natural fit here. Dan will describe how we interoperate with the HoloLens and showcase a simple app we've built where we use a classification model together with Azure Translator Cloud Services to place these augmented reality post-it notes on objects in the world to display each object's name in a different language. And then after that, I'll present one final presentation on interoperability. This time a preview of an upcoming feature which enables you to combine Psi with Teams. So Teams as in the remote meeting software we're all using a version of right now. In particular, I'll be talking about how we are able to integrate a Psi pipeline inside a Teams bot architecture to process video and audio streams from all participants in order to prototype intelligent meeting experiences. So here we'll show a simple demo sample on how you could use a Psi Teams bot to show a little bouncing ball that tracks the most dominant speaker at each point in the meeting. And then finally, our last session of the workshop will be a preview of a higher level framework of components, representations, and inference models that we've been building on top of Psi, and which we plan to release an initial version of within the next few weeks, called Situated Interaction Foundation, or SIF. We're developing SIF to promote more research and development of physically situated interactive systems, which are systems that can reason about and act within some physically situated context and interact with and around groups of humans in the open world. So that would include, embodied virtual agents, social robots, and so on. And I'll explain more about what I mean by all of that and show a little bit about what you can do with SIF in that session. So that's just a quick preview of what you'll see over the next 2 days. I hope you stick around and chat with us throughout these sessions. We'd love to hear your comments, discussions, and answer any questions you might have along the way. Okay, but for now, let's move right along to the next session. So Eric Horvitz is going to share some opening remarks about Psi, including some of the original goals, history, and broader context for why we started working on Psi in the first place. Eric is, of course, the Chief Scientific Officer at Microsoft, but he's also one of the original founders of the Psi project. He's been a huge supporter and champion of Psi from the very beginning, has been very deeply involved. So let's go to those remarks now.
Thanks for joining us for the workshop on the Platform for Situated Intelligence, Psi. I'm Eric Horvitz, Microsoft's Chief Scientific Officer. I'm also a founding and long-term collaborator on the Psi team. Psi has been a journey. A great deal of passion has fueled the effort, passion about possibilities for developing and fielding new kinds of interactive, real-time AI systems. We've been particularly interested in the development of AI systems that can work in a collaborative, fluid manner with people. I'm pushing on the frontiers of human-AI collaboration and human-robot interaction. To date, the AI community has barely scratched the surface given the possibilities. There's great opportunity ahead to make progress on several fronts, including making advances on understanding human-AI complementarity, on raising the fluidity with which AI systems coordinate with people, and on achieving mutual grounding, on endowing AI systems with the ability to develop shared understandings with people about the task at hand and the overall situation in which people and machines are jointly immersed. Now, achieving these goals will require systems to perceive and make sense of streams of information across the multiple modalities that we depend on as humans to understand the world, that we depend on when we solve problems and when we work with one another. The SCI effort was born amidst challenges we encountered with the pursuit of human-AI collaboration advances within the Situated Interaction Project. Within this effort, we've sought to endow systems with the abilities to see, listen, and speak, and to leverage multiple sensory feeds to understand critical aspects of language, gestures, and the surrounding physical environment. We learned a great deal over the course of several multi-year system building efforts, including the receptionist, the assistant, the directions robot, and the third generation elevator projects. These multimodal efforts have all relied on integrative AI solutions, solutions built via the weaving together and coordination among multiple AI competencies to support multiple and continuous loops of perception, reasoning, and action, including perception and inference about a system's own actions and their effects on the world. We've made good progress with principles and results over the course of the situated interaction effort. We also learned a great deal about the hard engineering challenges with building, debugging, and extending multimodal integrative AI systems. Learnings include the difficulties with grappling with widely different timings and time constants of signals and processing across different modalities like vision and speech, and the different delays that come via processing of components that are employed to analyze and fuse inferences. Timing issues are amplified with the stacking of inferences into pipelines of analyses. The timing challenges are compounded in that completion times can be stochastic and non-deterministic. On another pain point, common debugging techniques, such as tracing and breakpoints, have not provided efficient means of gaining insights into failures with large-scale, end-to-end integrative AI systems. Now, motivated by experiences with building these systems and the goal of enabling faster-paced progress on multimodal systems and applications for human-AI collaboration, the team decided to pause to do a deep dive on the creation of the SCI framework. The effort has focused on developing a distributed execution infrastructure that supports asynchronous processes of perception and inference. The team defined core data structures that make it efficient to represent and reason about time, as well as the key constructs of space and uncertainty. That is, time, space, and uncertainty are first-class objects in the system. The team also put special emphasis on providing new kinds of debugging capabilities, including rich visualizations. And as part of building up the breadth of core capabilities, the SCI team set up what is now a growing ecosystem of components. On another front, and one that at the foundations of integrative AI, SCI's time-centric runtime provides opportunities for doing new kinds of systems-level learning and optimization. There's great opportunity to harness machine learning for meta-reasoning and control of integrative AI systems. For example, to employ deep reinforcement learning to dynamically guide trade-offs on the efficiency versus accuracy of the analysis of streams of perceptual data. SCI provides access to valuable handles for data collection about system operation. This kind of meta-level learning and decision-making from these kinds of data sources can be a pathway not only into the optimization of specific applications, but a window into research on principles of integrative intelligence, for exploring approaches to the orchestration of perception and reasoning. Now, in the most recent work, the SCI team has been introducing higher-level data structures and programming abstractions, adding constructs to the system on the grounding of understanding, attention, and the guidance of conversation, and these will be useful across a multitude of human-AI collaborative tasks. Before ending, I'd like to share a reflection about the promise and necessity of integrative AI approaches moving forward. There's been a great deal of quite appropriate excitement about the power of deep neural network models. The jumps over the last decade in vision, natural language, and speech recognition have been awesome and surprising, and we're now seeing advances in building multimodal neural models that leverage joint vision and language data sets. These developments will play an important role in advancing human-AI collaborative abilities. However, I don't believe the challenges with rich, fluid, multimodal collaboration between humans and AI systems will be handled magically and in a solitary way by one or a few deep neural models. For the foreseeable future, we'll need to do significant work on the coordination of multiple AI competencies and components to engineer systems that can perceive and make sense of events, people, and surroundings, and to take sequences of actions in coordination with the actions, needs, and understandings of people. Making progress will depend on advances in both scientific and engineering capabilities. We've reflected about this chasm between where we are today in human-AI collaboration and the truly stunning advances in AI for performing singular vertical tasks like object recognition and speech recognition. One source of this gap, we believe, is that we have not had good tools and methods for building and debugging integrative AI systems, as rich integrations of multiple competencies are going to be required for these solutions. We hope that Sci can help to close the gap and to speed progress for helping researchers and engineers to address intrinsic complexities of building and debugging multimodal integrative AI systems. I'd like to end by thanking all the attendees for spending time at our workshop and hope that you'll find the information valuable. The workshop will cover the runtime that provides a foundation for working with streams of data, tools that enable debugging, data visualization, annotation and analysis, and the growing ecosystem of components, sensors, analysis, and effectors, including components that wrap a diverse set of technologies. It's our hope that you'll find the Sci framework useful for innovating and creating, and that you'll contribute to refining and extending Sci. We thank the teams already making contributions to the code base. For folks new to Sci, we look forward to your engagement, feedback, and contributions to the framework. The shared intelligence and efforts of the broader community is so valuable for supercharging the power and vibrancy of the Sci code base, and for pushing on a shared vision on building and fielding rich multimodal systems. Thanks very much.
Everyone on the same page. This is actually content that we've prepared for a webinar with broadcast actually last fall. So it's possible some of you on the call might have already seen some of this material if you've attended that webinar. I think it will be a good refresher. And also, again, we'd like to make sure that we bring everyone up to speed. There's two parts to this. I will start with just a high-level overview of the various parts of the framework, as Eric mentioned, the runtime, the tools, and the components. And after that, we'll take a really quick break to check if there are any questions. As I mentioned in the introduction, I would encourage you guys to ask questions in stream as you see things on the slides as the presentation goes by, and we'll try to get to them. After the quick break, we will go into a second part of this, which involves a coding tutorial that will show you how to write a quick, simple application using Sci. And again, hopefully we'll give you a sense of what programming with this framework is like and whether it is something that might be useful in your own work. So with that, let's roll the framework overview. Platform for Situated Intelligence, which we sometimes abbreviate as \PSI and pronounce like the Greek letter Psi, is an open source framework that simplifies development and research in multimodal integrative AI systems. These are systems that leverage different types of streaming data, such as audio and video and depth information, and that integrate and coordinate multiple types of AI technologies to basically process this data in real time. So a prototypical example in this space might be a robot that uses cameras and microphone arrays to try to understand the world around it and engage in an interaction with coordinated speech, gaze, gesture with multiple people to, for instance, give directions inside a building. Building a system like this obviously requires a lot of multimodal audio-visual processing and leveraging different kinds of AI technologies, speech recognition, computer vision, dialogue models, behavioral controllers for gestures, so on and so forth. Now, this system is at one end of the complexity spectrum, and Sai as a platform was developed in part to support development for this kind of rich multimodal systems that do a lot of intensive processing and have many different components. At the same time, the scope and reach of the framework is actually much broader. Basically, anytime you are dealing with temporally streaming data, or if you need to bring together multiple kinds of technologies, and especially if you're in a situation where you're latency constrained or where acting in real time matters, the affordances that Sai provides can accelerate development. Over the last years, we've seen a lot of fast progress with machine learning in a lot of perceptual AI technologies. However, building end-to-end useful systems of this nature is quite a daunting engineering task. And in part, the problem lies with the fact that the fabrics and programming languages that we use to build these systems are missing important primitives and are not really well attuned to this type of task. So Sai as a platform was developed to address these challenges and simplify development for this type of systems, whether they're social robots interacting with groups of people in public spaces, intelligent buildings, instrumented meeting rooms, mixed and virtual reality systems, all the way to applications that use simpler, smaller devices like a Raspberry Pi or some IoT sensor, but that still do stream processing. So now that hopefully we've clarified the scope of the framework, let's talk about the outline of the rest of the webinar. So I will start by discussing some of the challenges with building these kinds of applications in a bit more detail. After that, I want to give you an overview of the main aspects of the framework to get you familiarized with some of these principles and tools and affordances, and for you to get a sense about whether this would be something that might be useful in your own work. Following this overview, we'll do a bit more of a deeper dive into actual coding. I want to do a hands-on tutorial and show you how you might write a first application with this. And again, we won't have a lot of time to go into the detail, but the idea is to give you a feel for what programming with Sai is like, and for you to be able to understand whether this might be something useful, again, in your own work. The tutorial will take about 30 minutes. At the end of that, I will give you more pointers to some documentation and resources. And then I want to bring the conversation more to how you might get involved. As I mentioned before, Sai is an open source framework, and we're looking forward to really creating a community here and getting more people engaged to help us bring this to the next level. And at the very end, we'll have a live Q&A session. Okay, so let's get started from the challenges. Well, to a large degree, many of the challenges with building these systems stem from their multimodal and integrative nature. These systems work with different types of streaming data, so audio, video, depth, LiDAR, pose tracking results, speech recognition results, so on and so forth. This data is generally streaming at different bandwidth and with different latencies. And it's typically processed in these complex pipelines that bring together many kinds of components built out of heterogeneous technologies, right? You might have anything in these pipelines from, sensor-specific device drivers to cloud services that induce a certain amount of latency, to deep networks that run on GPUs and other kind of GPU processing, to application-specific logic and code and interaction with databases, so on and so forth. Now, these systems tend to be pretty compute intensive, and they often need to operate under latency constraints. And so performance considerations are quite important. Oftentimes, you want the systems to behave well under load or under latency, and properties such as graceful degradation of performance are often a requirement. Now, Even if you leave aside the challenges that stem from the sheer complexity that these systems have, and from the fact that they use these heterogeneous components and they have these stringent performance requirements, a number of other challenges arise from the fact that the programming languages and the fabrics that we use today are missing an important set of primitives, are not well attuned to this kind of applications. For instance, notions such as time, space, and uncertainty are core in a lot of these systems, yet these are not first-order objects in any of our programming languages today. And as a result, a lot of time ends up being spent developing low-level infrastructure issues. Take, for instance, time. I've already mentioned that these systems need to be fast, but being fast is not enough. Coordination actually requires being latency aware. Oftentimes, these systems need to perform data fusion, where a component needs to integrate information coming from different pathways. Well, to do this correctly and in a reproducible manner, the information arriving on these different streams needs to be paired according to when those events happened in the world, not according to when they reach this component, because that might be affected by latencies in the system and so on. And so in the absence of the right primitives, a lot of efforts ends up being spent on building this kind of infrastructure and debugging low-level issues rather than on the task at hand. Finally, I would argue that these applications also have a specific set of needs when it comes to debugging and data visualization and analytics, which are not sufficiently addressed by the development tools that we have today. So for instance, debugging these complex concurrent applications with breakpoints and printfs is not really scaling, is not really effective. At the same time, other aspects such as data visualization, the ability to inspect and visualize these data streams as they flow through the application, and the ability to run queries and perform data analytics can significantly speed up the development cycle. So Psi as a platform was basically built out of a desire to address these challenges and basically to provide the right kind of infrastructure and tools and components to accelerate development for this kind of multimodal integrative AI applications. The main goal of the framework is to lower the engineering costs basically and foster more innovation and research in this space. And we're open sourcing this framework because we believe success in this space really hinges on building a community, on bringing together expertise and know-how from different areas, and ultimately on building a thriving ecosystem where we can leverage each other's work. The framework is cross-platform, works both on Windows and Linux, and it's built on .NET standard. So it's a managed framework that retains the affordances of a managed programming language like C#, so things like managed memory and type safety and so on, while aiming to address the performance requirements that these applications often have. At a high level, Psi provides three kinds of affordances. The Psi runtime provides infrastructure for working with multimodal temporally streaming data, and it provides a parallel coordinated computation programming model that simplifies writing applications and components in this space. There's a set of tools that are centered on data visualization, annotation, and data processing and analytics that accelerate the development cycle. And finally, the third part is an ecosystem of components that wrap different technologies and allow you to quickly prototype and foster reuse. So over the next few slides, I'd like to give you a brief overview of each of these areas. And I'm going to start by talking about how Psi applications look like and what are some of the affordances that the Psi runtime and low-level streaming infrastructure provide. So Psi applications basically are pipelines or graphs of connected components that talk to each other via streams of data. I have a fictitious pipeline here where there's a microphone and a camera. Let's say you're trying to detect who out of many people in an image is the one talking. So you take the audio from the microphone, pass it through a voice activity detector that tells you that speech is happening. Similarly, the images from the camera run, let's say, through a lip movement detector, and then you try to put these two signals together to figure out who is talking, who is the speech source. Now, writing these kinds of applications, wiring components together, is very easy to do inside. The code on the left-hand side kind of illustrates this simple fictitious example. It takes about one line of code to create a new component and one line of code to connect two components together. Now, once you call the run method on the pipeline, the Psi runtime actually takes charge of executing the pipeline. So it schedules the components for execution, and it starts flowing messages on these temporal streams of data. The streaming infrastructure in Psi has a number of very important properties. First of all, streams in Psi are strongly typed, right? They're based on .NET generics. You can stream any type of data. You are not constrained into only using certain specific data types. And you get things like type safety. Now, more importantly, though, is the fact that time is really a first-order primitive, a first-order construct in the Psi streaming infrastructure. So each of these messages that are flowing through the streams are timestamped not only with a creation time, which is when the component that generated that message created it, but also with something we refer to as an originating time. This time is assigned at the source when the message first enters the pipeline. So for instance, when the camera first sees an image or when the microphone picks that particular bit of audio. And the important property here is that this originating time is automatically carried forward throughout the pipeline as the message goes downstream, which means that each of these components can basically be latency aware because they know what the time is when they receive the message, and they have access to this originating time information so they can find out the latency of the message. And this latency awareness throughout the entire graph enables a number of important scenarios. One of these scenarios is synchronization and data fusion. For instance, this component here, this speech source detector, knows that these two messages arrive at these specific latencies. So as messages arrive, it can buffer them and pair them according to when they happen in the world as opposed to when they arrive at the component. In fact, Psi provides a large number of primitives that support this kind of synchronization and data fusion, interpolation, windowing, all these time-related operations, and eliminate the need for the developer to think about how this exactly needs to be done, how much things need to be buffered, how things are coordinating. Rather, the developer can just use these primitive operations and compose an application and focus on the task at hand. Another important property of the Psi streaming infrastructure is that data can be easily logged. Logging is a very important aspect in these applications, a core piece of functionality, and Psi enables it in a very easy manner. You can just apply a .write stream operator on any of these streams and send the data to disk. The framework automatically generates custom serialization code, so you're not bound into any specific types. You can basically log most .NET data types. And the fact that the timing information is persisted together with the data means that we can enable another very important scenario, which is reproducible replay. So for instance, you can eliminate the sensors in an application and resurface the streams from a previously persisted store and rerun your application in a reproducible fashion. So you can tune the application, turn various knobs on the downstream components, and improve them to get the results that you want. This kind of reproducible experimentation is an important accelerator in this space. There's a number of other affordances that the Psi runtime provides, and I don't have time to go into all of them in detail here, but just as a high level, the runtime, just like the components, also has access to the latency information. So that opens up interesting opportunities in terms of how the runtime does scheduling to get pipeline parallelism efficiency and to maintain things running at steady state. It also enables developers to control how the application behaves under load. So for instance, application writers can specify on which streams information may be dropped and under which circumstances and which of the messages can be dropped, and so on and so forth. I Don't have time to go into detail into all these aspects here, but there's a lot more documentation on the GitHub site where you guys can learn more about this. Now, so far we've talked from the perspective of an application writer. Oftentimes when you develop SCI applications, you hopefully will be able to reuse off the shelf a large number of components, but chances are you will also have to write your own components that are specific to your own application. The SCI framework makes writing components also easy. So for instance, if I want to write this speech source detector, all I have to do is write a class for this component and implement two so-called receiver methods, one for each incoming stream, right? So when a message arrives on this stream, the voice activity receiver method gets called, and similarly when a message arrives from the lip movement detector, then the respective method for receiving that lip movement gets called. That's pretty much what it takes to write a component, and then from inside the receivers you can post messages downstream to send them out on the component output. Now the SCI runtime provides a couple of other important properties here, and one of them is state protection. What I mean by that is that you can define your own state variable, like for instance this time since the person last spoke variable here. And you can touch this variable from both receivers. You can write to it and read it from both receivers without having to lock it or worry about concurrency issues. When the SCI runtime schedules the various components in the pipeline for execution, it tries to maximize pipeline parallelism, so we will execute receivers of different components in parallel on multiple threads. But it will always ensure that the receivers of a given component are executed exclusive with respect to each other. So this exclusivity is enforced automatically by the runtime, so you don't have to worry about concurrency. You can program this component as if you live in a single threaded environment, even though when it's put in an application and run as part of a pipeline, it will run concurrently with many other components. So this is a property that simplifies component authoring, and it couples to another important property, which is isolated execution. Whenever one of these receivers receives one of these messages, it can actually modify it and edit it and touch it and manipulate it internally however it wishes. Because if this message is being sent to a number of other receivers at other components who can also touch it, the SCI runtime automatically ensures that everyone gets their own copy. So there's an automatic cloning mechanism implemented that again insulates the component writer from the intricacies of a concurrent execution environment. Finally, another important property here is that you can easily hierarchically compose subpipelines into higher level components. And this type of hierarchical composition, of course, helps with encapsulation and with keeping the code simple at the top level. But the other important property here is that when the runtime executes this, each of these individual components still run as individual subcomponents, so we still get fine-grained pipeline parallelism from a runtime standpoint. And so this programming model fosters, in some sense, using a lot of small different components that execute in parallel and avoid some of the traps of growing large monolithic components. So hopefully this has given you a sense of what are some of the main principles and affordances in the SCI streaming infrastructure and runtime. And with that, I want to switch gears and talk a bit about tools. Well, in the space of tools, we've put a lot of accent on data visualization. Specifically, SCI provides this application we refer to as Platform or Situated Intelligence Studio, or in short, SCI Studio, that enables users to easily visualize data from collected by SCI applications. So you can open one of these stores that was persisted by SCI applications, and with simple drag and drop operation, create these complex composited layouts. In this case, I have a visualization from a sample application in which a user can point to various objects in the room, and the machine tries to detect and understand what these objects are. You can have timeline visualizers, so things like audio, numerical streams, speech recognition results, At the bottom there, there's a latency visualizer. You can have 2D visualizers like images overlaid with object detection results, histograms, and so on. You can have 3D visualization, so you can easily look at sort of point clouds, rotate around the image, visualize various kinds of other 3D objects like tracked bodies and camera views and so on and so forth. You can easily navigate over time, and you can inspect various values that streams take over time. You can easily zoom in and out, and you can adjust which region of the data you're viewing. There are a number of ways in which you can navigate basically in the data, and the tool makes it pretty easy. You can also play back sections of the data, and you can do that at regular real-time speed and listen to the audio that was recorded, or you can play back things at a faster speed or at a slower speed if that's of interest. Now, apart from all this support for visualization, another important aspect here that the tool provides is data annotation. So here someone's demonstrating actually creating annotations for which objects this person is actually pointing to. This is a very useful affordance in a lot of these systems when you're trying to either generate annotations for machine learning or maybe to tune and understand the behavior of your application. All of these visualizations can be done offline based on data that was previously pre-recorded, but also live as demonstrated here. So you can open the tool and connect to a store that is being actively written to by a live application, and the streams will show up live and you'll see what's going on moment by moment in the system. And you can even drop out of live mode and scrub through the data and then catch back up with whatever it is actually playing. The framework also has support for working with large data sets. For instance, here someone demonstrates a data set with multiple sessions. So as your system runs and you get multiple sessions, you can accumulate these in a data set. And then you can do data processing. For instance, here we're running a batch processing task for generating new acoustic features. And then the streams that get generated from this batch processing task can be visualized in line with everything else. Finally, in the long run, we're planning to develop fully interactive capabilities here where you can write short snippets of code and directly interact with and manipulate with your data from code and see it as you write in a read, evaluate, print kind of loop. So hopefully this gives you a sense of the data visualization and annotation tools that are currently available in the framework. And with that, I'm going to switch gear to components. The components currently available in the GitHub repo focus a lot on multimodal sensing and processing. So there's a number of components there for sensors, like cameras and microphones and other kinds of sensors like the Azure Kinect or Intel RealSense. There's components for processing audio and imaging data, and there's components for doing things like speech and vision and language processing. There's also components for running machine learned models, for instance, Onyx, DeepNets, and also wrapping a variety of cloud services, Azure Cognitive Services. The idea here is that we are providing the seeds behind what we hope to be a growing ecosystem of components. I think success happens here when we're able to leverage each other's work. So we're hoping more of you will get engaged and contribute your own components in this space. The other thing I would like to say here is that while Psi is an open source framework, it's not just open source, it's really meant to be an open and extendable framework and to interoperate easily with other kinds of ecosystems. So for instance, ROS is a framework that's very frequently used in the robotics community and provides a number of important affordances. Well, Psi can easily bridge to ROS, and it's possible to create hybrid systems. For instance, imagine a social robot where navigation is done via ROS nodes and components, whereas the social processing part of it is done with Psi components. The framework interoperates with many other ecosystems. You can use ZeroMQ as a transport and various kinds of data formats to interoperate with things like Python and JavaScript and Unity and so on. And we continue to evolve this. Again, the core idea is that the framework is meant to be open and extendable. So this brings me basically to the end of the framework overview. Hopefully this has given you a sense of what are some of the main capabilities in the framework, some of the main tools, and whether this is something that might be useful and interesting in your own work. Hi guys. This is Dan Bahush again. Thank you for listening in on this session. We're going to now go to the Q&A session. We've tried to answer a couple of questions that have arisen in stream. I guess one of the questions that we often get is what kind of computer should I use, when I build systems with Psi. Psi was designed. The runtime is pretty lightweight, and it was designed with a target machine in mind, like a normal modern multi-core desktop machine. But we've run it all the way down to a Raspberry Pi, and there's also a remoting story that lets you create pipelines that are distributed, running across multiple machines. For instance, if you have multiple cameras, multiple sensors, then you might need to create a multiple machine system. Another question I saw pop up in the live event is whether we have any plans to integrate this with Azure Percept. Definitely an interesting thing to consider, and we're going to look into that more. We don't have anything to announce on that right now, but there's certainly interesting connections there, and we'll take a closer look. We have built a number of bridges to different ecosystems, and like I just said, as an open source project, we are trying to make it connect easily to a lot of other similar ecosystems or places where you would want to kind of connect. And so Azure Percept is one of those places that we will look more into. I'm going to try to look through the chat to see if there's other questions. Yeah, or Sean, if you have other questions that...
So there was a question about, in the example you showed, like what camera, LiDAR, microphone system were you using? Was that a Connect 2?
Yes, so that example is, I'm assuming you're referring to the pointing example with the what is that application. That example was based on an actually Azure Connect camera. And there's a sample in our repo, so we can put a link to the samples in the chat. But basically in our samples repo, we have a number of these examples. You can find that entire sample app there. I should also say that while that app in that particular case, I think, if I remember correctly, was built based off on Azure Connect, we do have components for Psi for Azure Connect 2. So if you happen to have an Azure Connect 2 device, there are existing Psi components that let you use that device.
There was a question also about, are there any commercially available alternatives? I assume they mean to... Actually, I don't know if they're talking about Psi or if they're talking about the sensor at this point. But maybe that's a good question about what are the similar infrastructures out there? Like, is there anything even close to Psi, or is there, what are the kinds of things out there that are?
Yeah, so I think, one thing that comes to mind is definitely, in the robotics community, especially ROS, similar kind of, in some sense or in intention, kind of framework that lets you build this kind of integrative systems that leverage many different kinds of components. There are a number of important differences, though. The devil's in the detail. When you look at frameworks like this, there are a number of important differences between Psi and ROS and what each of them have been kind of geared towards and optimized towards. And we'll actually have a session, I think tomorrow, on interoperability with ROS, so we can discuss more in the Q&As there. But that's definitely one framework that comes to mind in that direction. But yeah.
And then there's a lot of questions streaming in now, so I'll just keep asking. We'll have to stay on time, but let's see. How about interoperability with traditional monolithic applications? Like, is there any guidelines on how to interoperate with some of these other, like, say you already have some big application written in some other thing?
Yeah, so Ashley will actually talk tomorrow. We have a whole that's on interoperability. In that session, like, he will talk about how to interop with an application that's written Python on the other end. But really, it's Psi provides sort of support for interoperability. Now, this assumes you have control of the application on the other end. It assumes you can kind of inject code in the other application. But Psi provides a bridging framework using this 0MQ infrastructure, which is very common and has, I think, surfaced in many different programming languages. So if your application on the other end that you want to interface or interoperate with has, the ability to kind of do 0MQ, then it's relatively easy and straightforward to connect with AI. Actually, throughout the day tomorrow, we'll have a number of these interoperability story. One would be towards Python, another one towards HoloLens, another one towards Teams. So I recommend watching those sessions. It will give you some ideas. But if you have more specific technical questions, I guess also always I want to point people to the GitHub repo and encourage you to open issues there and ask questions. If it gets into more actual technical details of how do I do this specific interoperation.
Yeah, and that already answers, I think there was a question about do we already have integration with Teams? Check back tomorrow. We have a whole session on interoperation with Teams, sample coming soon. I also want to make sure we have enough time here. I don't know, someone should stop me. And we can keep answering questions in the chat. And also there's another Q&A break at the end.
I see another quick question here that I want to very briefly, can we run it on OS X?
Yeah.
I'm not sure, Ashley, if you know the details exactly of that, but what I wanted to mention is, Sai is a .NET framework, so anywhere .NET Core runs, basically Sai will run, I think. I'm not exactly sure about OS X, but we can get back to that, I think.
Yeah, I think we've seen examples of it running on OS X.
Okay.
On Mac.
So let's then move to in the interest of time, let's move to the coding session. We will have a bit more Q&A time after that, before the break, and we'll try to answer some more of the questions that arise in chat. Thanks so much, guys.
Question, Dan. Sorry,
yeah.
One question that it did come up, given that this is the coding tutorial we're going to, they're wondering, would you recommend that they try to follow along with the tutorials? If so, should they be on Windows?
I think in this particular session that's coming up next is going to be like 20 minutes or 25 minutes. I think it will be pretty difficult to follow along just because we're kind of moving fast and we're switching between the coding and the actual explaining the coding, the actual tools. I think the most useful thing would be to watch it at this point. Mm-hmm. The samples are available in the repos, and these sessions will be recorded and we'll make them available. So you can always come back to them and go more slowly at your own pace, through it and with a code side by side. You could try it, but my recommendation again would be just to watch it. It will be kind of like a nice exposition, and hopefully it will give you a good idea, and feel free to ask questions. Yeah. Cool. So let's go to that session.
So as an example, we're going to build a voice activity detector. It's going to be a very simple one. We're going to take a rather naive, simple approach, but the goal here is just to illustrate how programming with Sai works like. So a voice activity detector basically determines when in an audio signal there is speech or not. And to do this, we're going to start by using a microphone component. We're going to capture audio with that component, and then we're going to pass this audio to another Sai component that does acoustic feature extraction. Now this component generates a number of different features, and we're going to look at one feature that's called log energy that kind of reflects the amount of energy in the signal. So the more noise there is, if someone is talking, the energy will be high, and otherwise it will be low. So we're going to just try to threshold this signal to recover basically the blue signal, the blue binary signal. That's the voice activity detection signal. And we'll do a bit of more processing on it, but that's the basic idea. Now, this is a very kind of naive way to build a voice activity detector, but it will be sufficient to demonstrate some of the capabilities of the framework. And once we do that, just so that I really showcase the fact that you can build rather more sophisticated applications, and we can quickly prototype something that's much more complex and that does bring together many different kind of AI technologies. I want to very briefly, in a couple of minutes, talk about this other sample application written a couple of hundred lines of code, where a person can point to objects in a room and say, what is that? And the computer tries to determine which object is being pointed to, sends the cropped image to an object detection service, and tries to understand basically what the object is that the person is pointing to. Okay, so let's get started. I'll be using Visual Studio 2019 Professional Edition, but you can also use the Community Edition or VS Code, which also works on Linux, or for that matter, any editor of your choice. I'm going to start by creating a new project, and this is going to be a C# project console app.NET course. I'm going to hit next here, and then I'm going to call it Simple Voice Activity. As I hit create, Visual Studio will take a couple of seconds and generate a basic project structure for us. Now, there are basically two ways in which you could start coding a Psy application. One approach is to use the Psy source code. As I've already mentioned, Psy is available on GitHub, so you can go to github.com/microsoft/Psy and clone the repo. You can then build a solution where you link your application against the Psy source code and build it all together. The second approach, which is what I'm going to use here, is to use NuGet packages. These are binary packages that we provide with every release and that speed up development. As you don't actually have to build a Psy codebase in this case, you just link against these packages, and this is an easier path if you don't plan on actually modifying the Psy codebase. So I'm going to do that here, and to add these NuGets, you go to Dependencies, right-click, Manage NuGet Packages. You'll have to make sure that this Include Pre-release checkbox is marked because the Psy NuGet packages are still in beta pre-release mode. And then I'm going to go to Browse, and the first package I'm going to look for is called Microsoft.psy.runtime. This package contains most of the core bits for the Psy infrastructure, so you'll use it in all your Psy applications. I'm going to hit Install. It brings out a number of dependencies, and then I'm going to accept this license, and the package gets installed. Now, since in this sample we'll be doing some work with audio, the other package I want to install is called Microsoft.psy.audio.windows. This package provides Windows-specific APIs and components for things like microphone capture, audio processing, acoustic feature extraction, and so on. So I'm going to install this one as well. Now, at this point, you may be wondering, how do I know which packages do I actually need to install when I write a Psy application? And this is where I'd like to point you to our documentation. So our documentation is at our website on github.com/microsoft/Psy and is accessible via the wiki. Now, on the right-hand side here, there's a sidebar with a lot of pointers to various parts of the documentation, and we'll go through some of this in a bit more detail later, but for now I just want to point you to these two pages. The first one is a list of NuGet packages, and the second one is a list of components. The list of NuGet packages shows you all the different packages that are currently available, together with a brief description about what functionality they provide, as well as information about whether the package is running on Linux or Windows, and what kind of CPU platform the package is built for. On the list of components, you can find more detailed information about all the components that are available. They're grouped under different categories like sensors and imaging and vision and so on. And there's information about which package each component is provided in, and also a brief description about what the component does and information about the platform. So these two pages, the list of NuGet packages and list of components, can be very useful in the early stages when you're trying to discover basically what's available. But let's now get back to actually writing the application. So I'm going to start by adding a couple of using statements that will give us access to the packages we just added. So using Microsoft.psy and using Microsoft.psy.audio. Now, as we've previously discussed, Psy applications consist of pipelines of components connected to each other via streams of data. So the first thing we'll have to do is create the pipeline. This can be done easily by means of a factory method called pipeline.create, which we can invoke to get back this pipeline object. And to run it, you can simply call the run method on the pipeline, but in this particular case, I'm actually going to call this a sync version of the run method, because what I want to have happen here is I want to start the pipeline running, then I want to wait until the user presses a key. And once the user presses a key, I want to actually stop this pipeline. And inside, to stop a pipeline, you have to call pipeline.dispose. So this is pretty much all the code you have to write in order to create and run a pipeline. Now, of course, this pipeline is at this point empty. It has no components in it. So let's start next to add some of these components. And just so that you don't have to wait for me to type, from now on, I'm going to try to directly paste some code blocks that I've written, and we'll discuss them line by line. So these 3 lines of code basically create a microphone, an acoustic feature extractor, and connect the two together. The first line creates the microphone by simply creating a new instance of this audio capture component class. Every time you instantiate a component in Sai, you have to pass it the pipeline object. And in this particular case, I'm also passing a configuration parameter to specify that I would like this audio capture component to generate audio in this specific format. Similarly, the second line creates an acoustic feature extractor by instantiating the corresponding component and passing the pipeline object. And finally, the third line connects the two together by using this pipe2 operator. Now, in general, in Sai, each component has a number of outputs, or so-called emitters, that produce streams of data, and a number of inputs, or so-called receivers, which receive the streams of data. And the pipe2 operator can connect emitters to receivers. In this case, the microphone component happens to have a single output called .out, and the acoustic feature extractor has a single input called .in. So normally this code should look like this. I am piping an actual emitter called out to the receiver on this other component called in. However, since these two components have a single receiver and on this side a single emitter, the pipe2 operator works directly over them, allowing the code to be simpler and more readable. So this is pretty much how easy it is to create and instantiate new components and connect them together in Sai. Now, before I run this, I want to do one more thing, which is to add some printing information in the console so we actually see something happening as we run this little sample. Remember that we're interested in setting a threshold on the log energy feature from the acoustic feature extractor. So here are a couple of lines that actually print that information. So from the acoustic features extractor component, I take this log energy stream, and to it I apply this stream operator called do that allows me to specify an action to be performed for every message on the incoming stream. And the action in this case is specified by this delegate provided here that basically instructs the operator to print every incoming log energy value to the console. Now, this pattern of applying operators to stream is quite common in Sai, and we'll see a couple more examples shortly. But for now, let's just run this. So what we can see is that the log energy values get displayed, and you can kind of tell that the values are low if I stay silent, and then go higher if I start talking. So let's stop this. So you've noticed probably that the printouts come pretty fast, and that's because this do operator executes on the cadence of the incoming messages from the log energy stream, which in turn is generated by this acoustic feature extractor component in response to messages from the microphone component. And this one generates audio buffers on a fairly fast pace, I think every 10 milliseconds or so. So what I want to do is slow that down, and the way I will do it is by injecting a stream operator here in front of the do operator, and this is the sample operator. So I'm going to sample this log energy stream on a specified cadence, say about every 0.2 seconds. And that way, the next do operator will only work over these more sparsely sampled messages. Now, when I run this again, we will notice that the cadence of the printout has slowed down. So now we can more clearly read it and see that the values are relatively high when I'm talking and lower when I'm not. Okay, so the next thing I'd like to show you is how to actually persist streams to disk and how to visualize them. Data logging is key in a lot of these applications, and Sai makes that very easy. The first thing you'll have to do is to create a store in which to log this information. And in Sai, you can do this again with a factory method called SaiStore.create. And I'm telling it the name of the store and the path where to put the store on disk. And then to write these streams to disk, you simply use this other stream operator called write. So here's 3 lines that are writing the microphone stream and 2 streams from the acoustic feature extractor, the log energy and the zero crossing rate, to the actual store. I have to specify names for each of these streams. So this stream, I'm writing it under the name audio. This one is log energy, and the third one is called zero crossing rate. So when I run this again, it will behave just like before, only that now the streams are actually written to disk. Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. So if we go now to the temp folder, you notice here there's a simple voice activity.0000 folder that was created. And in here, there are a couple of files that all together form the store in which we have persisted these streams. The persistent system in Psi is optimized for throughput, and you might see multiple data files in a store like this, plus some index and catalog files. Now, we will be able to actually visualize this data, and to do so, we will use Psi Studio. This is a tool that comes with the Psi framework. You'll have to build it actually from the Psi code base. I've already done that build, so I'm going to just go ahead and open it. So Psi Studio is an app that lets you visualize multimodal data. You can open the store that we just created in the temp folder, and you can pick any of these files. Psi Studio figures out that all together they form a store, so you can select any of them and open it. And the tool will display the streams available in that store: audio, log energy, and zero crossing rate. You can visualize these streams by dragging them in the visualization container in the center. So here's the audio, here's the log energy, and I'm going to drag the zero crossing rate and overlay it here with the log energy. Now, Psi Studio lets you construct fairly complex visualization layouts with multiple panels and overlaid visualizers. And the structure of these layouts is displayed in this tab here. So we see we have 2 timeline panels. One contains a visualizer for audio, and the other one contains 2 overlaid visualizers for log energy and zero crossing rate. The panel on the right-hand side shows properties for visualizers, panels, and streams. So here, if I select zero crossing rate, I see the properties of this visualizer, and I can actually change colors and various other aspects. So for instance, here, I'm going to change this to a darker color because we're less interested in the zero crossing rate. Then I'm going to select log energy, and I'm going to change this to a brighter orange color and maybe increase a bit the line width. Psi Studio lets you also very easily navigate over the data. You can actually zoom in with the mouse scroll wheel and zoom out. And you can click inside this panel and drag the timeline to the left or to the right. At the top, there's a navigation bar that provides some more information about timing. The entire black region at the top represents the entire store, and this gray highlighted portion of it represents the portion that's currently in view, and I can select that and move it around, so I can move the view across my store, and I can also adjust its edges to basically adjust the portion of the data that I'm actually seeing. You can also select portions of the data and play them back. Testing 1, 2, 3. Testing 1, 2, 3. And actually you can do that at different speeds. But for now, I'm actually going to remove this selection and zoom back to the level of the entire store. So what we'd like to do here is figure out what threshold we should pick for this orange stream to construct our voice activity detector. And so we'd like to inspect some of these values. And you can do so by right-clicking here and then selecting Show Legend, which will display sort of a live legend that as you move your cursor over time, it will update those values. So you can see that high values are in the range around 10 and so on, and low values are around 1. So for now, let's just pick something in the middle, let's say 7. And let's go back to the code. Now, to create this voice activity stream, I'm going to actually use another stream operator called select that allows me to transform a stream by applying a function. The function I've specified here is one that returns true if the log energy is greater than 7. The resulting stream will be a stream of Boolean values, and I'm writing that to the store as well under the name VAD. Now, before we go and run this, I want to show you another feature of the framework. Oftentimes, when you build an application, you may collect data from various sensors, like I've done here with the microphone. But then as you tune the application, instead of running it live again, what you'd instead like to do is rerun it over the same data that you just collected, perhaps many times in a row, adjust and tune parameters and see how the application responds and how you need to tune the parameters to get the behavior you want. So let's do that here. Instead of running it live again, let's run it over the store we just collected. So in the original application, the audio data was coming live from this audio capture component. So I'm going to remove this line, and I'm going to create that microphone stream instead by opening a store and opening the stream from that store. To open the store, I just use the scistore.open method, and I pass in again the pipeline, the name of the store, and the actual path where the store has been written. And to open the microphone stream, I call this openStream method on the input store. I tell it the name of the stream, which in this case is audio, and the type of messages in that stream, which is audio buffer. Everything else stays the same. But now when I run this application, the data no longer comes from the live microphone, but actually from the store that we collected a few minutes ago. Now, of course, this store is finite, and at some point the stream of data will terminate. There it is. I'm going to hit a key again and dispose the pipeline. Now a new store was just generated, so we can go ahead and visualize that inside Studio. So if I go to Open now and go basically in the folder above, there's a new session that was generated called 0001. So if I open this store, basically this will look the same because those streams have the same values, but now we have an extra stream here called Voice Activity Detector. So let me visualize this. Well, it kind of worked. In general, it seems to be doing the right thing, except that we have these little fluctuations up and down. And this happens because there's a lot of variance in the log energy stream and goes up and down pretty fast. And often there's small internal sort of dips or silences which we'll need to filter out. So basically, instead of switching from 0 to 1 and from 1 to 0, every time the log energy passes that threshold we have chosen, we want to move from 0 to 1 only when the energy has stayed at 1 for a while, and similarly from 1 we want to drop to 0 only if the energy stays below the threshold for a while. Now, in order to determine how long that should be, we need to get a rough estimate of what's the length of these drops. So I'm going to zoom in into one of these. And actually, SciStudio does have some tools that let you better understand and measure time. If you click these 3 clock buttons on the toolbar, the navigator displays some additional timing information. And now if I go and select a region, then I can see, for instance, here, where is the selection end relative to the selection start. So where is the red line, in this case, relative to the green line, to the selection start. And that is, in this case, about 177 milliseconds wide. So that's the width of this interval. And just to be safe, I'm going to choose a larger value, say around 300 milliseconds. So let's go back to the code now. So I'm going to paste another couple of lines here to create basically this filtered signal. And we'll take a look at them in a second. Actually, I have a couple of small errors here because I am using some link operator, so I'll have to go to the top and add another using clause for system.link. Now, if you look back here, these errors should have gone away. Yes. So here I'm using a couple of additional stream operators. The first one is called window, and this lets me buffer a window of messages. And in this case, I'm looking for messages in a future interval of 300 milliseconds. The second operator is an aggregate operator that lets me implement a stateful computation over its input, which in this case is this window of messages. So when using this operator, I have to specify the initial value for the state of the VAD signal that I want to produce, which is false at the beginning. And then I have to provide a function. This function has actually 2 parameters. The first parameter describes the previous value of the VAD computation. As I've said, this will be a stateful computation. And the second is the buffer of messages that arrives as an input to this operator. And this function actually constructs the signal. Basically, what this expression does is it says that if the previous state was false, then all the messages in the buffer window have to be above 7 in order for us to return true. And alternatively, if the previous state of the VAD signal was already true, then we can remain a true only if it is not the case that all the messages in the buffer are below 7. In that case, when all messages in the buffer are below 7, we need to return false. And then we're writing this stream to the store as well. So let's run this one more time, and remember that we're still running over the data that we've previously persisted from the store that we collected before. Only that now we're computing this additional filter voice activity detection signal. So let's go back to SciStudio. Now I'm going to zoom out again all the way to the session, and I'm going to open the new store that was created, one folder up here. And so now we have this VAD filtered signal, so let's look at this one. Okay, so this looks better. You can tell it's not actually quite perfect, like we're still missing some regions here. But as I've mentioned already, this is a very simplistic way to build a voice activity detector. It actually gets quite a bit more complicated if you want to build something that's really robust and reliable. The reason I've shown you though this small example is mostly to give you a sense of what programming with Sci is like, and about the visualization tools that you can use, and how you can iterate and save data to disk and replay from disk to fine-tune an application. Now, looking back at code, as you've seen, you can easily construct components and connect them to each other with this pipe2 operator. And there are many other operators that are available that let you process and manipulate streams of data. We've already seen some of them, like sample and do and select and window and aggregate. There are many other important affordances in the framework. For instance, the framework has operators that deal with temporal synchronization and data fusion. Or there are ways in which you can control how the application keeps up under load. For instance, you can configure whether, when, and which stream messages get dropped if there are not enough computation resources available. Components can be organized and aggregated hierarchically into sub-pipelines, and so on and so forth. I will actually point you in a second to more resources for learning about the various aspects of the framework. Now, this example we've worked on has been quite simple, and so before we're done here, I wanted to just briefly show you another example that's a bit more sophisticated, just to highlight how quickly you can construct more complex multimodal integrative AI applications. And I want to start by showing you this in SciStudio. Now, this store was collected with an application where we're trying to determine what object a person is pointing to. Let me take out this timing information and open the new store. Now, as I've opened this store, you'll notice that because the store doesn't contain any of these streams, they appear here with this yellow exclamation mark icon that indicates they're not currently available basically in this store. They're in this unbound state. In SciStudio, you can actually save and reuse various layouts you've constructed. And in this case, I've previously saved the layout that's specific to this new application. And to load it, I can simply select it from this drop-down list. Now, as you can tell, this is a somewhat more complex visualization layout than what we've worked with so far. Now, in this application, we have an Azure Kinect camera that's looking into a scene here. You can see the point cloud visualized, and this is a 3D visualizer. You can rotate around it. And we are doing body tracking and determining the direction that the person is pointing. We're intersecting that direction of pointing with a depth map. And we're taking this point and projecting it back into the RGB color camera and cropping a region around it. That's the image you see over here. And this image is being sent to Azure Computer Vision Service to perform object detection. The results from object detection are overlaid over the image. Finally, we're also using an audio capture component and voice activity detection, and we're cropping the audio in those regions and sending it to Azure Speech Recognition, which gets us back speech recognition results. The idea being here that a person could point to an object and say, "What is that?" and the machine would figure out what they're pointing to and respond accordingly. Now, obviously, an application like this is processing a variety of data streams, including depth, images, and audio. And we've glued here many different components, from Azure Kinect to custom-written gesture detection code. We determine, for instance, when the person is lifting their hand, this white signal indicates that, and only crop the region and try to figure out the target at those moments. And we integrate this with cloud object detection and speech recognition. Sai enables you to write such multimodal applications that leverage many AI components very quickly and in a very compact manner. And let me just really quickly give you a peek at the code for this application. So the patterns in the code are quite similar. We're creating a pipeline and a store to write the streams to. We're instantiating audio capture component, and in this case, for instance, Azure Kinect component that will provide streams for images and tracked bodies and so forth. And we're doing stream computations via a number of stream operators. One of the patterns that I wanted to quickly show you here is that you can write actually your own stream operators. Bodies here is a stream of bodies produced by the Azure Kinect camera, and this get closest body is a custom stream operator that I just wrote for this specific application. We've seen so far how Sai has a large number of operators that are generic, that operate over generic data types. You can implement your own operators. For instance, this one is implemented over here, and you implement them as an extension method for a particular kind of stream. So every time I have a stream that contains a list of Azure Kinect bodies, I can apply this operator. And the code of the operator is relatively compact, but it can be used as one line, which makes this readable here at the top level. And basically down below, we do some other computations with these streams. We instantiate the object recognizer and provided the Azure subscription key, and similarly with the speech recognizer. Basically, this whole application, up to instantiating and running the pipeline, is pretty much at the top level 100 lines of code. Now, there's these stream operators that I've just described that add maybe another 100 lines of code or so. But as you can see, this application can be written in a very, very compact manner. So hopefully between this example and the one we worked through in more detail before, this is giving you at least an initial sense of what working with Sai is like. Now, we didn't have time here to go into a lot of detail, and there's actually quite a bit more information available on the website. So next, I'd like to point you to some of that and orient you a bit around our documentation and resources. So as I've mentioned before, our documentation is accessible from the GitHub project wiki pages. And the sidebar on the right-hand side guides you through it. There's information about how to use and build the framework, either how to build new applications with NuGet packages or how to actually build the entire code base. And if you want to get started, the best place to start is the brief introduction tutorial. Now, this tutorial covers some of the topics we've already covered, but at the same time goes in a bit more depth and also talks about other topics, for instance, synchronization, and provides a number of pointers to additional readings and documentation on various topics that are relevant. So it acts basically as an entry point in the framework. And you can go through it at your own pace. Following this, I would recommend going either through some of the samples or through the tutorials. We have a number of samples, and they're described here. So there's a brief description with information about whether the sample runs on Windows or Linux. And also some of these samples have walkthroughs, so more documentation about how the sample was actually constructed. And again, these pieces of documentation point you to additional information and link into additional topics that you can explore in more depth to learn about the Sai framework. Going back to the wiki, the tutorials are also a good place to start reading as they provide a bit more of an in-depth overview of certain areas of the framework. So for instance, I would definitely recommend reading the tutorial on basic stream operators, which explain the family of operators provided by Sai. The tutorial on writing components that explains how to write new components. I haven't shown you any of that here. And other tutorials, for instance, understanding how the pipeline actually gets executed, or delivery policies which control the flow of messages and permit you to drop messages when the application may not be able to keep up. There's other topics on stream fusion and synchronization, merging, interpolation, and so on. So feel free to peruse all of these documents. They provide useful information about how to use the framework. There's also documentation for a number of more specialized areas under other topics. So for instance, how to do remoting. SAI supports constructing systems that are distributed, that talk to each other across machines, or how to bridge to other ecosystems like Python or JavaScript or ROS. And there's a number of other more specialized topics that are of interest to probably a certain population of developers. In general, there's quite a bit of information on the wiki. We'll continue to add more documentation and organize it in a way that's approachable. But also, if you feel there's a part of the documentation that's perhaps underdeveloped or you don't know how to do something, don't hesitate to just file an issue on the GitHub site, label it with documentation tag and say, hey, can you guys document this part more, and so on. So I think this brings me to the end of this brief dive into how to program with SAI. And let's go back to the slides.
Hello. So as I said, hopefully that was a kind of a quick whirlwind tour through what programming with SAI looks like. There's a lot more documentation. You guys can read into all the tutorials and the samples. Let's take more questions now, though, based on this session and the previous session. I think there are a number of new questions that have come in the chat.
There were a bunch of questions that came in the chat. We've been trying to kind of answer some in the chat. There are a few we haven't answered yet. There were a couple that were particularly about annotations. One about, like, can we use annotations to then go into Azure and train models and fine-tune models? And for the data annotation tool, can SAI automate the annotations, or does it only support manual annotations?
Yeah, so that dovetails really well actually with a session that's just coming after the break. So I think we're going to have a break after this Q&A until 11. But then at 11, I think, Sean, you're actually telling us about SAI Studio in more detail. So Sean will give a kind of a more in-depth view of SAI Studio, including the annotations part. So if you have questions around that, please stay tuned. It will be interesting. And you can actually, and we will demonstrate, we'll show like a quick example where, we can actually automate annotations or semi-autonomously generate annotations, and both create manual annotations or generate them automatically and then refine them manually. Annotations are treated inside just like any regular stream, so you can manipulate them in all sorts of interesting ways. Because of that, you can also export them. So to the question for Azure and uploading things like to Azure, generating annotations, and then going to Azure for training, that's also a possibility. There's a way you can write a very simple SAI pipeline that takes an annotation stream and export it into some format that you want. It might be something as simple as comma-separated values or something more sophisticated that then you can upload to your favorite tool of choice for training models and so on. But we'll see more about that right after this break.
Yep. Yeah, the short answer is yes and yes, like Dan said. The next session, I'm going to do a deep dive all through SAI Studio. The second half of it will be a lot about annotations, and we'll go through an automated annotation scenario. There's kind of a couple of other questions that were related. One that was about, does the system support calibration across multiple cameras and being able to integrate multiple viewpoints? And does the framework handle shared coordinate frames between multiple cameras or robots?
Yeah, so let's see. So on the first question, so definitely, SAI is as a platform, as a framework, is designed to kind of simplify writing of applications that work with streaming data, and cameras are one kind of streaming data. And of course, oftentimes you might have multiple cameras. So we actually are in the process of developing like a framework that kind of is more geared towards a specific kind of application that works, that's about perceiving, room size kind of environments and interactions with people in those kinds of environments. And as part of that, and we'll talk about that tomorrow, actually, I don't remember, I have to look at what time exactly is the session, but we have a session tomorrow on this toolkit for developing situated interactive applications. And as part of that, we'll talk a bit about, multi-sensor fusion from multiple cameras. We have not released these bits yet. They're coming out soon, but we are planning to release support for sort of doing fusion and writing pipelines that fuse information from multiple sensors, multiple cameras. Also, we would like to put out some calibration tools. There's nothing existing right now in the repo, but we have developed internally tools and hope to release them soon where you can calibrate multiple cameras and then just basically hit the ground running. The whole idea with the framework is that we want to simplify as many of these low-level tasks that everyone knows how long they take and how involved they are to do. You ideally want to say, I have these 5 cameras in these 5 locations and just go. And ideally, you want those locations automatically determined by some tool. So we're certainly going in that direction. It's on our roadmap. Stay tuned for the session tomorrow on this toolkit.
There was another good question that was about sort of synchronization.
Hello.
Lift him off my shoulder. So it's a question that Nick kind of had a very good answer for in the chat, but it's about, like, since these callbacks are called synchronously, how do we actually synchronize our multimodal data? I think it'd be good to kind of reiterate some of that stuff about, like, how does that actually use those timestamps? If you're trying to synchronize, like, your audio and your video streams, do the components register some time ranges which they can be treated as synchronous with the framework, or how does that work?
Right. So in this quick tutorial that we just gave before, that I was walking through, we didn't show any of this actually, but we showed a number of stream operators inside, like the select operator, and so on. So Sai has a number of these operators that are specifically geared towards data fusion and synchronization. And I think join is kind of the primary operator that lets you do that. So this is a stream operator that takes 2 or actually more than 2, like a number of different streams, and then pairs the messages that arrive on these different streams according to various kind of rules for synchronization that you can very quickly and easily specify. So by default, for instance, you might want to pair messages just that have the exact same originating time, right? If they travel through different parts of the pipeline and take different amounts of time to get to you, but they have the same source, you want to repair them back, based on the same originating time. But join lets you express much more than that. It actually lets you kind of specify an interpolator that kind of lets you do a range of things from, like, find the closest message to the current message, 500 milliseconds in the past and 10 milliseconds in the future. You can specify these relative windows. You can even do actual interpolation, like take 2 values that are nearby and kind of compute a value in between them, like a linear interpolator would do. And I think, as Nick probably said, like, we will have a session on that. He's talking about tomorrow morning in the first session, I think, about debugging and diagnostics. And as part of that, we're actually giving an example of, and explaining in a bit more detail how the synchronization operators work, and giving an example of what happens when things go astray and how you can diagnose when actually things don't go as you expect them to do, or when the synchronization is not happening as you expect it to do. And so, again, great question, but stay tuned for that. We'll definitely have more on that tomorrow.
Cool. And then there's a question that just came in about, again, like, is it possible to integrate data streams from distributed systems with Sai? So if you have, things that on multiple systems, and is there an example that kind of demonstrates that sort of distributed scenario?
So the answer is yes. There's many kinds of distributed system that I could imagine. So it kind of depends on what exactly you're trying to do. The general answer is yes. So let me say a few things. If you mean distributed system as in all the different pieces of the distributed system are Sai, right? So you have a Sai running on the machine and Sai running on a different machine somewhere else, and you want these things to talk to each other. We have a remoting story for this that lets you easily sort of ship the data around, and kind of get stream processing to happen, and everything is very natural. You get all the preservation of the data types, that are .NET serialized between these Sai applications kind of for free and so on. Now, if you want to couple in a distributed system a Sai application with a different kind of application, again, then you get more into this interoperability story where from Sai using 0MQ or something like that, you can ship data somewhere else. And Ashley will have a really nice presentation on how to do that with Python tomorrow, showing a full loop where you go to an application that's written in Python, and then you come back all the way in Sai. So, it bounces between the two. I guess so that's something else if the system is more heterogeneous. The other thing I should say is also, sometimes when people say distributed applications, I should make it clear, Psi was not designed, as I said before, the runtime is kind of very lightweight and designed mostly to kind of give you graceful degradation properties and kind of great CPU utilization, like, leverage the resources available on a single multi-core machines. You can connect 2-3 machines together. You can build a system in a lab where you have 4 computers running together, that all are distributed and talking Psi. You can certainly do that. Now, it's not really designed, like it wasn't designed and thought through for a scenario where you have like a cluster. Like I'm not talking here about like, 10,000 machines doing something together. Like it's not the kind of system that, at least it wasn't optimized and designed with that scenario in mind. The center of the target system is more like one multi-core machine, perhaps a couple of multi-core machines, and then scaling down all the way to like one of these perhaps Raspberry Pi devices. But you can certainly build some level of distributed solutions. Yeah, I hope that helps.
Yeah, I think so. I mean, I was going to kind of ask you, I think you already answered it about, what is sort of the sweet spot of Psi development?
Yeah.
Because there is kind of the whole spectrum from like lots of different machines that are linked together all the way down to like your little Raspberry Pi devices. So I think that answers a few questions actually. There's a question that just came in about how can we handle uncertainty in Psi? So would it be possible to have a stream of hypotheses and interpretations with probabilities for object identification and propagate those through the system?
Definitely very interesting. We actually thought that a bit, right? Like so that's on our roadmap. We don't have that right now released out there. It's a feature that we are planning to develop. And again, if you stay tuned to this session that's towards the end of the day tomorrow on this interactive toolkit that we're putting together, as part of that, we are evolving the core representations for even for time, right? Psi provides a lot of sort of representations for dealing with time at the streaming level, but we're evolving those even further to deal with temporally extended events and incrementality. We're evolving the representations to deal with space. So this goes back to the previous question about relative coordinate systems and cameras, multiple, that are kind of aligned and where things are relative to each other. And apart from time and space, definitely uncertainty is the third thing that's on our roadmap. And exactly.
I just want to reiterate, there's nothing preventing components now that can pass hypotheses around. The Psi is very, completely agnostic to the kinds of data. So any .NET types, any types that represent uncertainty can be streamed around, and you can write components that do inference and what have you on these uncertain representations. But I think what Dan is talking about is baking that deeper into the infrastructure, which is something that we're really interested in doing. And kind of letting uncertainty flow through all points in a pipeline automatically without you as a developer having to worry too much about it. So that's something that is definitely on our roadmap. There's another question here about kind of generally, what's the best platform to communicate the technical implementation of Psi tutorials or documentation with other developers? So maybe about how to teach this. I'm not sure either, but how to kind of maybe teach this to others, or what's the best set of resources and
yeah. So I think the
best way to teach it to other people.
I'll be very curious to hear. We have later today a panel discussion with a number of our previous with people that we've already engaged with in the external community. Some of these people have even taught classes with Psi and so on. So maybe they'll have some interesting things to say. I think in terms of documentation and resources, right? The webpage is our best spot. The GitHub website, the wiki specifically contains all the documentation. So there's a lot of materials in there that you can use. We'd love to hear from you what you think would be more helpful. After this event, we're putting some of these tutorials and videos we've created for it, out there. So they will also probably be able to serve as sort of getting started kind of material for people. But we'd love to hear from people, I think, what would be good to have on that side, right? We're so much on in our, we know this because we've been in it for a couple of years, and it's almost a bit hard for us to know what would be most useful for someone that's entirely new. And that's why I think we'd love to hear from you guys, thoughts. Yeah,
like Dan said, you're going to hear from some people in the panel session this afternoon, people who are not, in our immediate team that have used it out in academia and in the GitHub community. People who have used it to teach a class about interactive agents. So there are a few examples of people kind of teaching it to other groups of people, like even to students. But we'd love to collect more examples of that to hear kind of what works, what doesn't work, what are the barriers to get started, because we just want to make it as easy as possible for everybody to use this and share it. It is 10:45 now, so I think we should probably wrap up there. Dan, I'll let you wrap up our session.
Yeah, so thanks everyone for being here, and we'll have a break. I think is it 15 minutes? I think we're coming back. We're coming back at 11 Pacific Standard Time, and in 15 minutes, basically after a quick break, and then Sean will give us a nice walkthrough in more depth through SciStudio and all the tooling that's available, and that can simplify and accelerate your work with this framework.
We'll see you all in 15 minutes. Hi, everyone, and welcome back. In this session, we're going to take a deep dive into one of the most central and useful tools in Sci, which we call Platform for Situated Intelligence Studio, or just SciStudio for short. As before, please feel free to type any questions or comments you might have into the chat during the course of this session, and we'll either answer them directly in the chat or address them live in the Q&A portions of this session, which we'll pause for at about midway through and at the end. As mentioned briefly in the last session, SciStudio is a tool for visualizing the multimodal data streams that you might choose to persist from your Sci application. Being able to visualize various streams side by side in customizable layouts, from simple timelines to 2D images, 3D depth maps, 3D skeletal tracking, so on, is extremely helpful for debugging and iterating on the development of the applications you build with Sci. So in the first half of this session, I'll walk you through the basics of what SciStudio can do, including how to create, customize, and save simple visualizations of your data. In the second half of the session, we'll dive into some more advanced functionality and go over how to create custom annotations of your multimodal data, both manually and in semi-autonomous scenarios, which can really speed up the annotation process. Now, currently the SciStudio tool itself runs only on Windows, but it can visualize data stores which were created by Sci applications running on any platform supporting .NET Standard, including Mac and Linux. And SciStudio is not yet shipped as an executable, so you'll have to build it from the Sci codebase, and you'll find instructions on how to do that in our GitHub wiki. To show you some of the basic features of SciStudio, we're going to use a store of data generated from a small sample Sci application. So let me quickly go through what this little app does and what kinds of data it generates. As you can see, first we're creating our Sci pipeline like always, and we're creating a store on disk to write to. The first stream we generate is a large numerical sequence. Then we use select operators to derive new streams for the sine and cosine of the original sequence, and we write those sine and cosine streams to the store. We're also capturing video and audio streams from our webcam and writing those to the store. Finally, we're piping the audio stream to a voice activity detector and writing the output of that to our store. We've also enabled the collection of various pieces of diagnostics information in our pipeline, which is accessible via this diagnostics stream attached to the pipeline. We'll persist that to the store as well in case we have any performance issues we need to debug later. After we start the pipeline, it will keep running and collecting streaming data until we press a key to shut it down. Now, I've already generated a store by running this code a little while ago, so let's launch SciStudio and open that store we created. We'll see something like this. Before we get into all the ways we can visualize our data, let's first take a quick tour of SciStudio. At the top left is the Datasets tab, which shows us all of the streams in the store we just loaded: sine, cosine, image, and so on. Below that is the Layouts tab that tells us about the visualizers we currently have instantiated for each stream. Obviously, this is still blank at this point because we haven't created any visualizers yet. In the center is the Visualizations tab, where we'll be able to see the actual visualizations, and on the right is the Properties tab, where we can get more information about a stream or a visualizer and even configure various aspects of how each visualization is rendered. To start visualizing, let's drag the sine stream into the visualization area. Notice that a new visualization panel was added, and the data for our stream is now displayed inside it. We can use the scroll wheel to zoom in and out of our stream, and we can use the left mouse button to drag the stream across the timeline. Let's also drag the cosine stream into the same visualization panel. So that we can tell which stream is which, let's change the color of one of the streams. To do this, we just click on a stream in the layout panel on the bottom left, and the stream's properties will be displayed in the properties panel over on the right-hand side. We've selected the sine stream, and let's change its color to orange. We can also right-click inside the visualization panel and turn on the legend, which will show us the current value of each stream in the panel wherever we place the cursor. The panel we've created is called a timeline panel, which means that it shows a segment of data over time. Its x-axis is time, and the y-axis is the value of the stream at that time, corresponding to the current value on our timeline ruler at the top. The ruler shows us the elapsed time since the start of the session, but we can show more information if we need to. For example, if we click on the absolute timing button on the toolbar, we'll be able to see the current cursor time in absolute terms. And if we click on the timing relative to session start button, we'll see the offset from the start of the session for each message. As you know, each size stream is really a sequence of messages, and we can visualize the location of the messages themselves by right-clicking in the panel and selecting Show Markers. To get a clearer picture, we can drag the bottom of our timeline panel to make it larger, and then use the scroll wheel on our mouse to zoom in. We can also use the mouse to drag the timeline to the left or right. If we want to know the exact timing of the individual messages, we can right-click and select Snap to Stream, and now our cursor will snap to the individual messages. Then we can look at our timing information at the top to get the actual message times, and at our legend to get the values at those times. We can also change the interpolation style of our visualization, from direct linear interpolation to step interpolation, or we can select none to show only the messages themselves without any connecting lines. Streams can often be visualized in multiple different ways, and when we drag a stream into the visualization area, SciStudio automatically picks the visualizer that the tool deems to be the most appropriate. But if we right-click on the stream instead of simply dragging it, we can choose how we want to visualize the stream. First, let's create a new empty timeline panel by clicking on the New Timeline Panel button up here in the toolbar. Notice that this new panel has automatically been selected as the current panel, as indicated by its border being blue. If we now right-click the image stream, we can see the ways that it can be visualized. Notice that the first menu item here is Visualize as Image in New Panel. The In New Panel part is because SciStudio knows this stream is not compatible with timeline panels, and the current panel is a timeline panel. So if we want to visualize the images themselves, a new compatible panel will be automatically created for you by SciStudio. However, we can select Visualize Messages and Visualize Latency in the current panel, since these visualizers are compatible with timeline panels. So let's visualize the latency in a new panel. Let's turn on the legend so we can see the actual latency values, and we'll zoom in a bit so we can see the latency of each message more clearly. Notice that some of the lines are gray and some are highlighted in orange. If we look at the properties of this visualizer, we can see that there's a threshold we can set that indicates when our latency is higher than that threshold. So if we change the threshold from 50 to 55, we'll see that there's fewer messages that exceed the threshold. This type of visualizer can be very useful when we're debugging our Sci applications. So now let's visualize the image stream itself. But first, let's free up some real estate. We'll delete the sine and cosine visualizers, and we'll turn off this extra timing information. Now let's drag the image stream into an empty part of the visualization area, and a new panel will be created with the image stream inside it. So now we have two types of visualization panels, but they're not exactly the same. The top panel is a timeline panel, and its x-axis always represents time. As I hinted at earlier, timeline panels can display the data from a series of messages at once within some segment of time. In this case, we're seeing the latencies of all the image messages in the 4-second window we're currently zoomed into. By contrast, the panel displaying the video image is called a 2D instant panel. It's an instant panel because it always displays the data from a single instantaneous message from its stream at the current cursor time. And it's a 2D panel because it displays data in 2 dimensions. In the case of an image stream, the data rendered along the X and Y axes are the individual pixels of the image. Now, as I move the cursor back and forth, you can see the image visualizer displays the video image corresponding to the current cursor time. If you look down in the layout area, you can see that this 2D panel is contained in what's called an instant visualization container. This container can actually host several instant panels arranged side by side. And if I right-click in the panel showing the image stream, I can add a second cell to the right where I can add other visualizers if I wish. For example, if we now drag the diagnostic stream into this empty cell, we'll be able to see the diagnostic information. And we'll present a deeper dive into how we can use that complex diagnostics visualization to debug our SCI applications in a later session. But for now, we'll just get rid of it. We're also done with our latency visualization, so let's remove it from the timeline panel as well. We still have some other streams in our store, so let's drag the audio stream and the voice activity stream into our empty timeline panel, and we'll change the VAD color as well and zoom back out to the extents of the session. Now we have a bit of a problem here. If we turn on the legend and pan across the stream, we can see that our voice activity stream, which is a binary stream, switches between 0 and 1 when speech is detected, but the trace just looks like a flat line, and this is due to scaling. If we select this timeline panel in the layouts area and look at the properties, we can see that the y-axis goes from negative 20,000 to plus 13,000. So it's no wonder we can't see our 0 to 1 VAD transitions. And this is because by default, a timeline visualization panel will automatically scale its y-axis to fit all of the data currently visible. And that huge range is coming from the range of values in our audio stream. If we change the axis compute mode from auto to manual and set the minimum to 0 and the maximum to 1, now we can see that our VAD transitions properly, but of course now we can't see much of our audio stream. We can get around this by moving our VAD stream into its own panel so that it can use a more appropriate y-axis scale. So let's do that. We'll set the scale back to auto in this panel, then right-click and remove the VAD stream. Next, we'll drag the VAD stream into a new timeline panel of its own, and then we can drag this timeline panel up so that it's next to the panel with the audio stream. Now let's suppose that there's a particular section of our store that we want to select and focus on. If we hold down the Shift key and click somewhere on our timeline panel at the beginning of the desired section, we'll drop a green selection start marker. Then if we continue to hold down the Shift key and right-click in the panel at the end of the desired section, we'll drop a red selection end marker. Now if we click the Timing Relative to Selection Start toolbar button, we can measure the length of the selection we just marked out. This is a good way in general to measure time intervals in any timeline panel. We can also right-click in the timeline panel and zoom to the selection we just made. Selections are also used when creating annotations, which we'll be covering in more detail a bit later. Finally, selections are useful in controlling data playback from a store. If we click on the play button on the toolbar, we can watch while the selected portion of the store is played back in real time.
What day is this?
If we're currently visualizing an audio stream, that audio will actually be projected through our speakers as long as the playback speed is set to 1. We can play back the audio from any number of audio streams we have visualized at once. If we want to mute an audio stream, we can do so by right-clicking on the stream. We can also enable repeat mode here if we wish, so that the selected part of the session plays back in a continuous loop. Here is where we can speed up and slow down the playback speed. To clear the current selection, we can click on this Clear Selection button in the toolbar. Okay, we've spent quite a bit of time laying out our visualizations, and it would be a shame to have to do all this work again tomorrow. SciStudio allows you to easily save this layout to a file and easily switch between multiple layouts that we have constructed. To save the layout, we'll click the Save Layout button and give the layout a name. If we click on the drop-down list in the Layouts area, we can now switch to a different layout, create a new layout, and later on get our saved layout back again. Now let's take a closer look at our datasets area. So far we've concentrated on the streams in our store, so let's look at the other items in this tree. The parent node of our streams is called a partition, and it corresponds to the size store we created when we ran our Sci application. Above this node is the session node, and a session can contain any number of partitions. Suppose you have a complex setup with an application of several cameras around the room writing to one size store, and you have an autonomous robot application that's writing to another size store at the same time, for example. These two stores could be linked together to constitute a single session, because later on you'll want to combine the data from both of these stores in SciStudio to visualize and analyze them alongside each other. Finally, the parent node to sessions is the dataset itself, which can contain any number of sessions. The dataset itself can be saved to a file and reloaded as a single entity containing all the sessions and partitions that we put in it. Okay, so far we've been using SciStudio to examine and playback data from stores that we've previously collected. But we can also use SciStudio to look at the data from a live Sci application as it's being created. So to demonstrate that, we're going to first start up our Sci application again. And this time we're going to leave it running because now we're going to connect SciStudio to this application and visualize it live while it's persisting data. So back in SciStudio, we could open our live store in the usual way by going up to this button here and clicking Open Store. Which would create a new empty data set for the live store. Alternatively, we can add this live store to our current data set by right-clicking on the dataset node here, clicking Create Session from Store, and finding our live Sci store currently being generated by the running application. So if we go into this recordings folder where we're putting all of our stores, it should be the most recent folder in this directory. That's because every time we execute a new session of a Sci application, its store is placed in a new subdirectory, and it just increments this number at the end. So let's go into this folder here and select the store we find there. Now we have two sessions loaded, the session from the first time we ran our test application with existing data, and the new session containing the store that's currently being generated. Note that this new session is currently grayed out. While a SciStudio dataset can contain any number of sessions, only one session can be visualized at any one time. So let's visualize this new session by right-clicking on it and selecting Visualize. And now we're seeing our live session being visualized in SciStudio. Hello? I have the app connected to a different camera to the side of my desk here. Note that all of the streams here are now in light blue rather than the normal dark blue to kind of indicate that we're in live mode. And then of course the most important indicator up here is this live button that we see blue and activated, which tells us that we are in live mode. This also means that SciStudio is automatically scrolling the timelines for us as we collect data so that we're always seeing the most recent message for each visualization. And even though we're connected to a live store, if we see something interesting happen, we can leave live mode by clicking on the live button here in the toolbar, and now we go back into normal playback mode. We see it's still collecting data, and it's going to go off the end here. But now we can actually go back and scrub through our data as normally, zoom in and out, see something interesting. We can set start and end points and play that segment. So this is a segment of me from a few seconds ago. We can do all the normal things that we do when we're playing back data. And then if we want to go back into live mode, all we have to do is click this button up here again, and boom, we are back into live mode. Hello. So let's go shut down our Psi application. Let's tab over to that, press any key. And now back in Psi Studio, we actually see automatically that the store has been closed. It detects that that happened, and it goes out of live mode. And so now we are scrubbing through the data as normally. Okay, so that's it for part 1 of this session on Psi Studio and doing multimodal visualization. We've talked a lot about the basics of Psi Studio and how to visualize data, how to navigate through that data, how to create visualizations, and even how to go into live mode and visualize live data. So we're going to pause here really quick to see if there are any questions that we can answer live, and then we'll switch over into the second half of the talk, where we'll go deeper into some advanced topics in Psi Studio and talk about annotations. Hey everyone. So yeah, just as a reminder, please feel free to type questions into the chat during both of these parts of the session. In part 2, we're going to talk more about some advanced features of Psi Studio and go into annotations. But I don't see any questions now, so I think we'll go straight into part 2, and then we'll have more time for Q&A at the end of part 2. So let's go to that now. Okay, so in the second half of this session, we're going to cover a few more advanced topics in using Psi Studio, including how to annotate our data. For the remainder of this session, we're going to switch to a more complex store collected from a slightly more sophisticated application with several interesting streams in it. So let's switch to that store now. This is a store that was collected from the same sample application that Dan was talking about in the last session, where a person points to an object in the scene and the machine detects which object is being pointed at. Now notice that the contents of this store look a little different to what we had in the previous stores. Rather than a flat collection of streams, we just have 3 of these little squares instead: sources, pointing, and audio. And these are stream containers. If we open the sources stream container, we can see a number of streams contained inside it. If we click on the audio stream to view its properties, we can see that the stream is actually named sources.audio rather than just audio. Psi Studio uses a convention whereby a period in the stream name causes it to contain the stream within one of these stream containers. And we can use multiple periods in a stream name to create complex stream hierarchies. When you write your application, this naming convention enables you to group related streams together for visualization. Now let's take a look at our layouts panel. Notice that all of our previously created visualizers now have this yellow exclamation icon next to them. And that's because Psi Studio can't find the right data streams in this new store that can be bound to those visualizers. For example, if we click on the audio stream visualizer and view its properties, we can see that this visualizer wants to be bound to a stream named audio in a partition named demo, which is what we had before. Both the partition name and the stream name need to match for Psi Studio to be able to bind a visualizer to a stream. And in this case, the partition demo doesn't exist in this session, so the visualizer is left unbound. Luckily, we've already created a different layout that we can use to visualize this store. So let's switch to that layout now. This layout has several valid visualizers specified that match the streams in this store, which we see have now appeared. In the top left of the Visualizations tab, we see a new type of visualization panel. In the last section, we talked about timeline panels and 2D panels. This is a 3D panel, and just as its name suggests, it's able to display 3D visualizations. If we look at the panel in the Layouts tab, we can see that we have 2 visualizers in this panel. The first visualizer is rendering a Connect depth image stream as a point cloud along with a depth camera frustum in orange. And the second visualizer is rendering the Connect body into the scene as well. And if we zoom in for a second, we can see it there underneath the depth image pixels in blue. Now for 3D visualizers, we can zoom with the scroll wheel, we can rotate the scene by dragging with the right mouse button, and we can pan around by dragging with the middle mouse button. Now, like I said, this store was collected from a sample app called What Is That? And Dan introduced it in a previous session. It's available in our SciSamples repository online today. And the idea is to combine streams of RGB image, depth image, body tracking, and audio, along with image classification and speech recognition components, to classify the objects in a scene that a user is pointing to. And to do that, the application intersects the direction of pointing with the depth mesh to determine the object of interest. So let's make that a little bit clearer here in the visualization. First, let's hide the frustum, since we don't need to reference that right now. And now if we open the pointing stream container in our store, we can see we have a stream that was persisted named pointing line. If we look at its properties, we can see that it's a 3D line, so we can probably add that to our 3D scene. Let's drag it in, and that looks pretty good. It's showing us where the person is pointing, but let's change the color to make it stand out a little more. And we can do even better than that. If we right-click the pointing line stream, we have this option here called Expand Members. If I click it, SciStudio will perform reflection on the underlying type of the messages in this pointing line stream and show us the public members of the underlying objects in the stream. In this case, the pointing line happens to be a stream of nullable line 3D objects, and this type has a Boolean property called hasValue, as well as a value property that's of type line 3D, and that contains a valid line 3D when the hasValue property is true. So we can expand one more time this value property to now see the members of the line 3D, which include direction, length, start point, and end point, all the things that make up a line. While none of these submember streams were persisted explicitly by the application developer actually only persisted the pointing line stream to the store. SciStudio helps us dig into these members of the type and surfaces these members as if they were persisted streams, and we can visualize them just like any other stream. So that's really helpful for digging around and exploring different parts of our data without having to rerun and persist subparts of our data. So for instance, if we click on endpoint to see its properties, we can see that it's a point 3D. Let's now drag that into our scene, and it will get visualized as a sphere. We'll change its color to match the line color, and we'll make it a little larger. Great. Now if we scrub around the timeline, we can clearly see the point in the 3D scene that the person is pointing at. And you can use this expand members feature on any stream that was persisted. It's a powerful way to dig into your data and visualize subparts of the persisted types when necessary. And these members streams show up with an icon that looks like a smaller stream. Next, we're going to demonstrate how to create some temporal annotations over this data. SciStudio is great for creating annotations with temporal start and end points, where we can define a schema for what sorts of values can go in each annotation. And this is not a tool for doing more traditional image annotations, say, but really for any time you want to annotate temporal sequences of video, audio, or any kind of multimodal data that you've persisted in your Sci application. So in this example we're going to walk through, we're going to annotate the person's speech by listening to the audio stream, marking the start and end of each utterance, doing an open transcription of what was said, and giving it a finite label for the valence, basically how positive or negative the person sounded during the utterance. And maybe we're doing this annotation to compare to the speech recognition model that was running live. Or maybe we're using it to iterate on a valence detection model that we're developing from this data. There's lots of possible reasons for doing these kinds of annotations, and these are just a couple of examples. Okay, so first we're going to create some annotations to manually transcribe each utterance. In SciStudio, an annotation stream acts just like any other stream. After we've created it, we can do anything with it that we can do with other streams. So let's collapse the what is that tree to get some real estate back. Then we'll create our first annotations stream. To do that, we click on the Create Annotation Stream button on the toolbar. Now we have two options here: to create the annotation stream in the current partition, or to create a new separate partition for the annotations to go in. Basically to put it in the current store or to create a separate store. The text at the top of this dialog tells us that this decision can have a big performance impact when we want to save the changes we made to our annotation stream. And I don't really have time to get into the details of those choices. We'd have to go deep into explaining how size stores are actually laid out on disk under the hood. But suffice it to say that unless we're annotating a very small size store, it's usually best to place annotations in their own store. Because when we persist the annotation stream, the entire partition that it's a part of will get rewritten. So because this store we have here is fairly big with all of the images and depth maps in it, let's go ahead and create our annotations in a new partition, which will be more efficient when we're saving it. We'll need to type the name and path of the store where we want our annotations to go. Let's call the store name annotations test, and we'll put the store right next to our what is that store. We also need to give the stream a name, so let's call it classified utterances. Notice also the drop-down to select which annotation definition we want to use. Annotation definitions define the annotation schemas we're going to use for creating our annotations. And we'll talk a bit more about the structure of these annotation schemas and how to create your own in a little bit. But as you can see here, we now have a new partition named annotations test, and it contains a single stream named classified utterances. So let's go ahead and drag this stream into a new timeline panel. Okay, we've created our annotation store and we're visualizing our annotation stream, but there's nothing to see in our visualizer because the stream is currently empty. And that's because we haven't made any annotations yet. So let's start annotating some utterances. Looking at the audio stream now, these first two bursts of sound were just background noise made when the person first started the application. So we'll skip those and move on to this third one. Let's set the start and end selection markers to mark the extent of the utterance we want to create an annotation segment for, and play the audio to hear what was uttered here.
What is that?
Okay, sounds like the person said, "What is that?" Makes sense. So let's add an annotation by right-clicking on the stream and selecting Add Annotation. Notice that the annotation extends from the green selection start marker to the red selection end marker that we just marked. According to the annotation definition we're using, the top track should be the text of the utterance itself, and it uses what we call an unrestricted annotation schema, which means that any valid value of the underlying type is a valid value for the annotation instance. In this case, the type is a string, so any string is valid, and we can enter any string we want as the transcript. So let's change the value from hello world to reflect what was actually said by the person. And to do that, we just click on the text and type the correct value. The second track of our annotation definition is intended, in this case, to capture the valence of the utterance. Basically just how positive or negative did it sound. Again, this is just an example. You can set up your annotation schemas however you wish, and I'll show you how in just a moment. But in this case, the track uses what we call a finite annotation schema, in which each annotation can be one of a finite predefined set of values. If we click on the current value, we can get a pop-up with all the valid values we can select from. In this case, the person seemed pretty upbeat, so we'll set the valence to positive. Now, if we look at the properties of this annotation instance, we can see its start time and end time, and we have two more properties named transcript and valence. And these two properties correspond to the two tracks in our annotation. The top track is the transcript, and the bottom track is the valence. If we want to, we can change the values of the transcript and the valence directly here in the Properties tab, rather than on the annotation itself. Now let's add a second annotation for the next utterance. If we hover the mouse over one of the endpoints of the annotation, we can drag its start or endpoint like this. If we drag the edge of an annotation so that it touches the edge of a neighboring annotation, then they will snap together automatically. Now if we drag the edge, we'll be adjusting the start and end times of both annotations together. But if we hold down the Alt key when we drag, we can separate the two edges again. Now let's take a closer look at this annotation itself. Annotations in SciStudio can have any number of tracks, and in this case we have two. If we zoom into an annotation, then switch on markers and snap to stream, then we can accurately drag the edge of our annotation to exactly align with the VAD edges. If we look at the Datasets tab now, we can see that the annotations test partition and also the classified utterances stream have an asterisk next to their name. This indicates that the classified utterances stream, and by extension the annotations test store, have unsaved changes in them. So if we try to close SciStudio now, we'll get a warning that we have unsaved data, as well as a prompt to save it before shutting down. If we right-click the annotations test partition, we can see that there's an option to save changes, but we're not going to do that just yet. Let's take a step back now and look at what annotation definitions contain, and how one was used to define the schema with two tracks that you just saw. Annotation definitions are specified in a JSON file like this, and here's the definition we've been using. We'll be developing and releasing new features for SciStudio soon, such that you'll be able to easily create these kinds of annotation definitions from within SciStudio in the GUI, but for now you'll need to edit the JSON file directly. So as you can see, the file is named testDefinition.pad, and when SciStudio starts up, it looks for any annotation definition files in the documents/SciStudio/annotation definitions folder. Looking at the JSON itself, starting at the top, we have the name of the annotation definition, and in this case, it's called test definition. Next, we have a collection of schema definitions. Each schema definition defines a track in the annotation. If you recall, the first track in the annotation we created was a free text track, and you can see here that this track is named transcript, which is the same as the property name we saw for this track in the property windows earlier. All track schemas must be of type annotation schema of T or derived from it, and in this case the type is annotation schema of string. The isFinite annotation schema property is telling us that this track does not have a finite schema, i.e. it has an unrestricted schema. If we look at the default value property, we can see why when we added an annotation in SciStudio, the text was initially set to hello world. Finally, we have the metadata property, and this is where we set things like the border color, the fill color, the text color, and the border width for annotations in this track. Now let's look at the second schema definition. This was the one for valence. If you recall, valence was a finite schema, and it has a limited number of possible values. So this schema has a few differences to the one for transcript. Firstly, it derives from finite annotation schema of T, rather than from just annotation schema of T, and the isFinite annotation schema property is set to true. In this case, the underlying type is still string, but only certain strings are going to be valid. Then we have the metadata to define the colors, etc. as before. And finally, we have an additional property called schema values. As you expect, this is where we define all of the legal values for this annotation track. As you can see, we have the three values we saw when we added an annotation back over in SciStudio: negative, neutral, and positive. Notice, however, that the positive value also contains its own metadata property. In this case, we set the background to red and the text to white. In a finite annotation schema, each value may have its own unique metadata, and if you don't set such unique metadata, the value is rendered using the metadata defined at the top level of the schema. So there's a lot of flexibility in how your annotations are rendered. And that's the complete schema for the annotation definition we've been using. Again, this was just one example of an annotation definition that you could build for your own data and your own scenarios. And you can construct and use your own annotation definitions for now by starting with a JSON file like this and modifying it for your own purposes. Okay, so that's how annotations can be defined, constructed, and edited. But now let's talk a little bit about how we can actually speed up our annotation process by automatically instantiating annotation segments at the right spots with the right start and endpoints, so that we can sweep through them just to fill them in with labels, edit them, or delete them if we want. And this is possible because annotations are persisted just like any regular Sci stream, which means that they can not only be processed after the fact, maybe to aggregate statistics from them, but they can also be generated like any other Sci stream. So what we're going to do by way of example is use the VAD stream, the voice activity stream, to automatically generate annotation segments for utterances. So any place the VAD stream has a continuous value of 1, meaning that there is voice in that interval, we want to create an annotation segment automatically. And we can accomplish this by extending our SciStudio to include what's called a batch processing task, which will run over our data to generate the empty annotation segments before we sweep through them manually to refine, transcribe, and label for valence as before. But before I can get to that, I need to say a few words about the extensible nature of SciStudio. In this demo and in earlier ones, you've seen some cool visualizers, and you might be thinking, well, my data is a bit different from your data. Is there any way I can use SciStudio to visualize it? And it turns out that you can. Although we include quite a few standard visualizers with SciStudio, you can write visualizers of your own and plug them in. In fact, you can also write your own data importers for reading your own data in SciStudio, stream adapters, which let you translate from data from one type to another while the stream is read, stream summarizers, which can summarize data to improve performance, and also batch processors, which let you run an entire Sci pipeline on an existing store from within SciStudio. And we're going to build a simple batch processor now to help automate our annotations. So here's what the code for a batch processor looks like. Notice this batch processing task attribute on the auto annotate VAD stream method. When SciStudio starts up, it looks for any methods with this attribute in its set of loaded assemblies and marks them as batch processing tasks. Notice that this method takes in a pipeline object, a session importer object, and an exporter object. This gives us access to all of the streams in the current session, lets us run a Sci pipeline, and export our results to a store. The code inside the method is really simple. First, we just load the annotation definition we defined earlier. Then we instantiate a component we've called annotation creator that will actually instantiate our annotations automatically for us. Next, we open the VAD stream and pipe it to the annotation creator component. Finally, we write the output stream from the annotation creator. If we dig into the code for the annotation creator component itself, we can see that this code is also pretty simple. The annotation creator component is a consumer producer component, which means that it receives and consumes one type of message, and it produces or outputs another type of message. As you can see here, we're taking in messages of type bool, which we connect the VAD to, and we output messages of type time interval annotation. Looking now at the receive method itself, we're seeing that if the VAD is transitioning from low to high, then we remember that message's originating time for later. And if the VAD is transitioning from high back to low, then we have all the information we need to create an annotation with default values. So we create a new annotation with a time interval spanning from the VAD's low to high transition to its high to low transition, and we post that annotation out. Now, as I mentioned earlier, SciStudio looks for any available plugins when it starts up, so we'll need to restart it to make this batch processing task we wrote available. When we go to close SciStudio, it recognizes that we have unsaved changes from the annotations we created earlier, but we're going to be creating them again automatically, so let's just ignore that. No need to save these. So let's open up Windows Explorer and navigate to My Documents/SciStudio, where we're going to see a file named SciStudio settings.xml. This file stores all the settings for SciStudio, such as window positions and the current state of some of the toggle buttons, but it's also where we can specify all of the plugins that SciStudio should load when it starts up. Eventually, we're going to add features to be able to edit these settings and load plugins directly in SciStudio in the UI, but for now, we're going to need to edit this file manually. So this additional assemblies node is where we specify which plugins SciStudio should use. You'll see I've previously added a few DLLs here already, for example, for visualizers defined in the Azure Connect DLL, which we need for visualizing the Connect bodies you've seen. But let's add to the end of this list an entry pointing to the DLL for the auto annotator batch task we just created, and then save the settings file. Now let's start SciStudio up again, and notice we have this dialog listing all of the plugins SciStudio wants to load, and it's asking us to confirm that we really want these DLLs to be able to run inside SciStudio. We're going to click yes because we recognize all of these DLLs we've specified. Everything looks okay. If we open up our what is that store again, we'll be back to where we were before we shut down, except for those manual annotations which we didn't save. If we right-click on the session node in the Datasets tab, we see a menu item to run batch processing tasks. If we expand that menu item, we'll find the batch processing tasks defined in all the plugin DLLs we've loaded, and we do see one called auto annotate VAD stream here. So let's run it. As you can see, a new partition was added named auto annotations, containing a single stream also named auto annotations. Let's drag this stream into the visualizations tab and see what we have. And there we go. We have a stream of annotations that were automatically generated from the VAD stream's edges with the default values on all of the tracks of each annotation. Next, we would need to go through and edit the transcriptions and valence values manually, maybe refine the edges of some or delete other ones that don't truly correspond to spoken utterances, maybe because the VAD misfired. But having all these annotations added for us automatically like this will really make our task go much faster. And again, this is just an example of how we can use Sci to semi-autonomously generate annotations for us based on some auxiliary stream, like how we use the VAD in this case to generate utterance annotations. But you can imagine other examples, like if we automatically generated annotations from a stream that has a value of true whenever the person in the scene is pointing. And then we might sweep through and mark each of those annotations to classify the name of the object the person was pointing to, and so on and so on. But we found this functionality to be super useful, often when we're developing some inference model, then visualizing the results, annotating against it, computing performance, and refining and iterating from there. But that's all we have time for in this session. This has been a whirlwind tour through SciStudio, from core aspects of navigating through the UI, and all the way to annotations and batch processing tasks. Hopefully this gives you a sense of the power of SciStudio for visualizing and annotating all the rich data you'll persist with your Sci applications, and how that can really speed up the development cycle for your multimodal integrative AI systems. So we have a little bit of time left, and we'd be happy to answer any more questions you might have and discuss further. Thanks. Hey everyone. So like I just said there, please feel free to type more questions in the chat. We have some time here for Q&A. I'm going to start off with a couple of questions that we got from Akanksha and Willie that are kind of about the annotation tool itself and what's possible. Is it possible to collect multiple annotations for the same stream? And I think Willie kind of asked something similar, like, can you have independent annotations that aren't necessarily aligned as temporal segments? And the answer is yes. So in those examples, basically, you were seeing us create one annotation partition with one annotation stream, and each annotation stream is basically governed by one schema or one definition, which can have multiple schemas or tracks. So you can make these temporal segments with defined start and end times, and then according to your definition, it can have any number of tracks, which can have any number of labels. But if you want multiple kinds of annotations that aren't necessarily aligned, you can simply create more annotation streams that are governed by different annotation schemas, and then they can be totally, aligned in whatever way you wish. So then they're not completely linked. So it's possible to have any number of annotation streams with their own schemas, or it's just kind of this additional feature to have these single definitions that have multiple tracks, and you can keep things aligned that way. And then an important thing to point out is, again, that these show up in Sci as Sci streams. So like I showed there, they can not only be generated automatically in this kind of cool automatic way for you to then refine later, but to Akanksha's question, you can also do any kinds of processing after the fact on those annotations. So if you want to go into, write some code and write some components that can compute inter-annotator agreement across your different annotation streams, across different data sets, that is totally possible. I mean, we don't have specific components for that in the GitHub today, but I mean, that's totally possible to create and really any kind of processing that you might want to do over your annotations. Any kind of statistics that you might want to compute can be computed just like any other size stream. And then there's another question from Antonio that's about annotation hierarchies, like in Elan. I think I know what you're talking about. So that's not a feature today. We basically have what I just described. You know, you can make multiple annotation streams. They can have multiple tracks. Some concepts of like hierarchical annotations, that would be a really cool extension. We are hoping to extend this annotation feature in a lot of different ways. It's kind of a relatively recent addition to SciStudio. And so we'd love more community feedback on what kinds of features would you love to see in annotations. You know, is it stuff like hierarchies? And we, you know, there are lots of ways that we want to extend these capabilities in SciStudio. I mean, first and foremost, like I said, like one of the first things we need to do is make it more possible to kind of define and edit these annotation definitions and schemas right in the GUI, so you don't have to go to these JSON files. So that's definitely a feature that's coming. But if there are other kinds of extensions, like, you know, like these hierarchical annotations that people would love to see, we'd love to look into adding more of those features. I don't know, Dan, if I can't see if there's any other questions.
I haven't seen any other questions arrive. I think I was wondering if you might also say a little bit. So you showed these batch processing tasks way of, you know, kind of extending SciStudio to do some data processing. But you also mentioned that you can kind of extend it, of course, write your own visualizers, but also bring your own data. I feel oftentimes you get this question like, you know, you can do all of this over SciStores, you know, that are collected with SciApps. But what if I have my own data that's kind of temporal in nature and I want to do annotation over that?
Yep. Yeah, there's a few answers to that. Yeah, that's a question we get a lot. Like, you know, you have these size stores, right? And so these size stores are a very specific format for Sci that has been optimized for performant logging and throughput. So you can be logging data very quickly while you're running live, and it doesn't get in the way of your live application. And then we have these tools like SciStudio to read these stores specifically and visualize and do all the things I just showed you. But a question is, you know, let's say I want to, you know, export. I want to get this data into other formats, or I want to import. I have data in other formats, and I want to read it into Sci or visualize it into SciStudio. And we are adding more and more capabilities in both directions there. So, in the export side, you know, we have example components where you can go from Sci or Sci stores and export into like MP4s or into CSV files, or in fact, we have another tool, kind of like a little utility tool, like a Swiss Army knife tool alongside SciStudio called the SciStore tool that you'll find in GitHub, which you can do a lot of that exporting, actually. You can point it to different, you know, SciStores you might have on disk and export to different formats. And then in terms of like the import, in terms of the reading, that's another way that we've been extending things. We've actually added support for we call them third-party stream readers, and I think, Dan, maybe you can post a link to the wiki where we have some documentation on that. But basically, we have a pattern whereby you can implement stream readers for any kind of data type that you want, and we have examples. We have at least one example that's in the code today on how to import like WAV files. So if you have audio files in WAV format, we have examples on how to import that directly into SciStudio. So you can visualize your WAV files alongside your Sci stores. We're also working on more like an importer for MP4s directly, for example, which we hope to have out fairly soon, where you can show MP4 video files in your SciStudio alongside your Sci stores. And then, of course, like, you know, that can be extended in lots of different ways. We hope that, you know, this will be a pattern that other people can follow. So any format that you might have, it should be possible to implement a stream reader and an import for that. Oh, Dan, you're muted. I don't know if you're going to tell me.
It's bound to happen. Sorry, I was going to say that you kind of already addressed, I think, this to some degree. There's a question that came in from Chirag about, is there anything in the pipeline to connect the annotation tool to crowdsourcing platforms like mTurk? And I think, well, we don't have something that does it directly in a one pipe, you can certainly export, like you said, data, right? And
yeah, I would kind of be in this 2-hop way. You could certainly do that. You might need to write some of the glue following some of our patterns to connect that. But again, that would be a really cool extension that if that's something that people are interested in, and we'd love to look into it, support people who want to work on extending in that direction, because that's a real theme of like all of this is we want to make it very easy to connect. We don't expect everyone to just buy into only Psi and everything is Psi and like because there's lots of other ecosystems out there, other tools, people using MTurk, people using other kinds of annotation tools. So we want to be able to build these bridges and connect to other platforms and ecosystems, and the more the better. So we'd love to hear more ideas along those lines.
I guess it occurs to me, and I'm not sure if maybe Chirag's question was more about could we surface a UI like Psi Studio to like a Mechanical Turk work?
Oh, I see, that direction.
And I don't know, in that direction, I guess we have this WPF constraint right now. I don't know if you want to speak a bit more to that.
Yeah, so that kind of speaks to this issue, let's call it a known issue, that Psi Studio runs only on Windows because it's implemented for now in WPF, Windows presentation format, I guess. But a major ask and a major kind of wish list item for us that we want to work on is getting the Psi Studio to be cross-platform, to work on Windows and Linux and wherever, and to even then to work like in the browser, or to be able to integrate into like VS Code, for example, would be awesome. So there are ideas we have on how we can port to something like Electron or Node.js. It's just that that'll be a fairly major effort. We want to kind of think very carefully about what would be the right approach there. Maybe engage with people who want to get involved with that. But I think if we were at that point, which we really want to be, where you could, let's imagine, surface Psi Studio like in a browser window, that would open up so many applications like that, where you could send it to MTurk and have people in Mechanical Turk like annotating data for you. And of course, you'd have to figure out kind of where to put the data in a way that respects security, privacy, and all of that. But that would be super cool.
I think Chirag mentioned he has some interop idea on how we might go about doing that. So it would be fun to continue this conversation. I think we can do it either on GitHub or I think this is it's a good conversation.
Yeah, I'd love to talk more about that because I mean, I think we would just have to port some stuff. There are layers that we can separate in terms of what's in the interface and what's kind of in the layer of just handling data, serving up data and reading data. So I think there are certain things we can do to clean up that separation, and then it would be a matter of kind of porting away from WPF into something that's cross-platform, I think.
Trying to keep an eye if there are more questions here. I don't see anything else at this point, and I think we're close to time.
Okay. Yeah, so hopefully that gave you guys a good idea of kind of how to use Psi Studio, all the different features of it. Annotation is something we're really excited about, and like I said, it's relatively recent feature. I'm not sure if many people have used it yet, but we're hoping that people will kind of use it and let us know like how it goes, make issues in the GitHub, what works, what doesn't work, what features would you like to see, because that's something that we'd really like to support and extend going forward. But with that, I think we can end a minute early here. I think we have lunch now, right, for 30 minutes?
Yes.
So we'll have 30 minutes of lunch, or whatever meal you might be eating in whatever time zone you're calling in from. And we will be back at 12:30 p.m. Pacific time with a really exciting live panel discussion. We're going to have a bunch of people who have been longtime users and contributors to Psi from different communities. And we'll have a really exciting conversation about open source community. Cool. So I'll see you then.
So hi everyone again. Welcome final session for today, which is a panel discussion on basically the open source community around Psi. Now, when we set about building platform for situated intelligence, our main goal was basically to lower the barrier to entry and make it easier for all of us to basically develop faster in this space and leverage each other's work. And so the project is open source. What we would love to see is it grow. While the center of mass so far has been on and the effort has perhaps been at Microsoft Research, we have already seen the beginnings of a budding community around this project, and we'd like to have a conversation today about how can we better nurture and support that community and encourage you guys to basically come on board and help contribute and help us take this to the next level. And so we basically, that is the question that will drive the panel today. What can we all do to better support and grow the open source community around the Psi effort? And we've invited a number of folks from the existing community of Psi users and contributors. Daniel McDuff, who's been closely working with us here at Microsoft Research in a different team using Psi, Mohammad Soleimani at USC, Colin Stefanov, Monash Z at CMU, and Jason Wilson at Franklin Marshall College. And while we've invited them and we're putting them a little bit on the hot spot in the first couple of minutes to help us drive this conversation, we really want to engage with you as well in this discussion. So again, I'll strongly encourage you to put in your thoughts and your comments. This session is about you and about the community around this project and what can we all better do to kind of support and nurture and get ourselves aware of each other's work in this community. I'll kickstart it here. Let's switch back to a view of everyone on the panel. And I want to give next a couple of minutes to each of the panelists we've invited to briefly introduce themselves, tell us a little bit about how they've been using Psi and perhaps what they found very easy or good about it, and also one thought about what we might do to improve things. And let's start with Daniel.
Thanks, Dan. My name is Daniel McDuff. I'm at Microsoft Research, and we've been using Psi primarily for building sensing systems. So a little less on the kind of interaction side and more on the sensing side. We want to build systems that we can deploy at scale to build things like dashboards that help people reflect on their affect or emotions over time, build systems that kind of respond to people's affective states with different types of interventions. And so to that end, we've been building components mostly focused around understanding physiological states, nonverbal behavior in terms of facial expressions and gestures, and a little bit on voice as well. And for some of these components, we would really love to be kind of consumers of things that already exist because they're, state-of-the-art models. And then some of them, these are models that we're bringing with our own kind of expertise, particularly in the physiological sensing domain, as well as understanding facial expressions. To me, I'd love to see ways for us to be able to kind of collaborate more across groups to build these components, and also find ways to kind of document the data sets that we use to train models that go into different components and ways to characterize those things so that people using the models have maybe a bit deeper understanding of their performance than you might typically get with a model zoo or something like that, because I think the Psi offers a lot of rich capabilities, and if we can reuse components and really understand kind of how they perform, that would be beneficial to a large number of people.
That's great. That makes a lot of sense. Thanks a lot, Daniel. So let's go next to Mohammad again, a couple minutes, and then we'll bring up the discussion eventually to everyone together.
Hi, Mohammad Soleimani. I'm from the Institute for Creative Technologies at the USC. My research is about emotion recognition and behavior understanding. And at ICT, at our institute, we are very much interested in using interactive technologies for training and education. So a lot of what we do in terms of more applied research requires building systems that can work in real time, that can generate interaction reports, so that it can give feedback to the trainees or students. And we have been using Psi for kind of human behavior sensing. So similar to what Daniel mentioned, we are also interested in kind of being able to use the system to record people's reactions in experiments. And what Psi, how Psi helped us was that it lowered the barrier in terms of like us actually having a good tool. In the past, we used SSI, which is another open source platform, but maybe in bit much less capability, and Psi just kind of supercharges what we can do and makes it much easier for us to focus on maybe what we're better at, and to just build like new interactions, new experiences, and just kind of focus more on our research. Psi has been very helpful to us, and we have developed like a multimodal sensing platform that is that uses all open source components that we have shared. It's called OpenSense. So if anybody's interested, they can access it. We are hoping that it should be released soon under BSD, but for the moment it's research only. But that has been partly my problem. I've gotten all the permissions now from lawyers, but I still have to do some paperwork myself after the semester is over and my teaching is done. I will do it, and then it will be BSD, and then we can also publish nuggets. So that will make it, I guess, easier for people to use.
That's great to hear. Thanks, Mohammed. Colin.
Hello, hi Dan. Thanks. My name is Kalin Stefanov. I'm from Monash University, and my research is around the problem of like analysis and modeling of multimodal and multi-part interactions. So I've been looking for something like Psi for many years, and I was very happy to find back in 2018 about Psi, and I've been following all the developments around the platform, and I'm really impressed with how far it went for the last couple of years, and all the things that are actually down the pipeline and being shared now during this workshop that are coming out, like new features and new capabilities. Psi helped me a lot actually in building like this very complicated, complex multimodal and multi-party systems where you have a lot of sensors and a lot of processing of those input signals and a lot of delays and dealing with what to pair with what when you make a decision, especially in the multimodal context when you rely on data from several sources. Historically, I needed to do that like in an ad hoc way. So based on the system that I'm gonna build, I'm gonna like implement some very complicated way of actually synchronizing and make everything like fit together. Psi just completely removed that part of my problems. So I can, as Mohammed already said, I can essentially concentrate on looking into the individual components and optimizing those components. For example, some kind of a neural network which makes some kind of recognition or detection or something like that, instead of really going into the details of the implementation and the and how to actually make the whole system work together as a whole. Which is coming from Psi essentially. And as Mohammed mentioned, we were working on extending essentially the components layer of Psi with some new components, and this led to publishing this other platform which is called OpenSense, which is as well open source. It essentially just extends the components layer of Psi. It's completely compliant with Psi and especially the main functionality of Psi. It follows the whole system and just offers some new components which people might find useful and can reuse for their own research.
Great. Thanks, Callan. Let's hear a few comments from Z as well.
Oh, hi. I'm Z. I'm a final year PhD student at robotics at CMU. So my research has been looking at like how people interact with like multiple robots, in particular when they kind of interact with one robot then another. So all my research has been very interaction heavy. So it's like, how do you make sure the robots do stuff immediately in response to different behavior responses? So like I'm doing a study right now, and I kind of use Psi as like the sensor integrator. So like by multiple Azure Connects, and I use Psi to kind of merge all of them together, do processing on it, and able to make sure that the time there's not big delay. And then I pipe it to ROS, where it actually do control the robot. So I kind of work with the interop of the whole Psi system, which is really nice. It's actually surprisingly easy to just send it over. I've been spending more time in ROS to fix stuff than in the Psi side. Then my plan is actually, and I'm using it right now, is like I would read all the data again in Psi Studio to analyze it, making sure everything is working correctly. And then our lab also have just released like a third-party reader, so you can actually look at ROS bags in Psi Studio, which is really nice. I think they added that functionality last year. So like I could pipe in everything that both written in ROS and written in Psi, put it together, and kind of see, all right, how much is the delay in this part? Where is stuff having trouble with? Also, kind of visualizing everything. I really appreciate Psi Studio because in ROS you can never scroll backwards in time, so it's kind of nice to kind of scroll between places to do things and say, all right, that's where the person had trouble with, and then all right, let's fix it. And instead of like playing it again, which is how you do it in ROS.
Cool, great to hear. So Willie.
Hi, I'm Willie. I'm Willie Wilson, and I'm at Franklin and Marshall College. And my research really looks at interactive systems. I've looked at human-robot interaction, particularly in the area of socially assistive robots. I also look at other sort of assistive agents. And my work really is kind of away from the sensory components. All right, so it's kind of very different from Mohammed and Daniel that are very much looking at the sensory aspects. And I care a little bit more about the reasoning once I've kind of sensed this. And because of this, my expertise is not in the sensing. I don't want to spend a lot of effort understanding how to make the sensing work. I just want to take components and use them. And so I've really been happy to use the Psi pipeline to be able to piece together these different components and not just use the components that Microsoft has produced. I've reached out to my fellow panelists, and my fellow panelists have been kind enough to actually provide me with some of the components that they've been building in Psi, and I've been able to integrate that into my systems as well. So that's one thing about that I really appreciate about not just Psi, but also the community that we're starting to build here. The other thing is I've been integrating this into the classroom, and so I've have multiple undergraduate projects that have used Psi so far. I have one that's going on right now. I've also integrated this into a seminar course where we did a semester-long class-wide project. So I had 25 students all working together on the same project. Basically, each group got assigned a different component, which was a great way to kind of divide up the project. Everyone could kind of work on their own component. I could provide them data stores so they could actually evaluate their own component in isolation to everyone else. And a key thing this class-wide project working was tutorial videos. So the team, the Psi team's done a great job of producing a lot of tutorial videos. When I did this, there weren't quite as many tutorial videos yet. And so I went ahead and produced a handful of tutorial videos. Some of them were specific to my project, but some of them were just how do you get started with Psi and how do you kind of use Psi Studio? Some of the stuff that we've actually been seeing today, and I'm actually interested in expanding on that. I plan on doing a lot more projects, especially with students and undergrads, because I'm at an undergrad college, and I want to be able to allow them to get up and running very quickly.
That's great to hear. That's great to hear. I will actually put a pin into this. I want to come back to this topic. There was actually a question. I don't know if you guys were on the call earlier today about like what are the kind of materials and how can we disseminate this and what's the best way to teach people about this. So I'd like to bring the conversation for sure back to that point about the classroom and how can we use this in education as well, just to teach about multimodal interaction or interactive systems, any of these areas where this can, like you said, kind of simplify work. And so I'll come back to that. I think there were a number of other topics that were brought up. That's great. I also want to highlight, I asked the question quickly in the chat with the audience for other folks to tell us how are they using Sai. And I think one answer came from Matthias, who's using Sai to record and analyze co-located brainstorming sessions, and the data is used to implement implicit interaction and automated moderation. So again, one of these scenarios where it's kind of data collection plus then probably some sort of processing or maybe creating sort of interactive responses. So I think one thing that kind of stood out to me in the guide made is that, we have a bit of versatility here, which I think is good, right? There's this sensing side and maybe data collection side to things. Like you're saying, really, if I want to do something that's higher level, I can just ignore the sensing problem because to some degree, some of these components perhaps solve part of that for me. But I think one question that kind of I have more is like, and then Mohammed alluded to it a bit with even the licensing thing, I guess relates to it, is like, this component ecosystem, right? For this to be successful, I feel we need to get to a point where there's enough components out there where when most people go to it, they find 80% of what they don't want to worry about in some sense already there and done. And so I guess a question I have is how do we organize things so that people can find out better about these things so that they can know about the open sensing that Mohammed has been building and the tutorials that he has, and so on and so forth. And by the way, this is a question I'm curious what you guys think, but for the audience as well, please type in the chat if you have ideas about things we can do from our end, at MSR and on the GitHub side or as a community altogether to kind of build more awareness. Because one concern I have is that, I might know two of you and this person might know that person, but how do we get from where we are today to a place where people can find this more easily? So I'm curious to hear ideas about that, both from you guys and from the audience. Any thoughts on this from the panel?
Oh, I can go first. So I came from the ROS world, I guess, because I do robotics. ROS is like sort of the de facto in like robotics. Like if you create a robot, there's always going to be a ROS component somewhere there to do it. Like people ask, like I've been in meetings where like people ask if there's a robot, it's like, all right, does it have a ROS layer? So in ROS, I think there's ability to easily find the components. There is a website where like all the components are sort of listed if you're in like this gigantic repo. And I was thinking back to this inside, I think the one challenge here is that components are smaller than a package. Like you can have a component. So then the question then becomes like, so for our lab, we have a separate Git repo for, I think we call it tbd.sci.components. We have multiple components inside, but how do we expose that to other people is we're not too sure how to do it. And then I think that's a general question, like, do we have to have different GitHub repos, or it would be nice to have like a centralized place to look for these things. I think ROS have that as like a searchable thing. So maybe we need to have some kind of centralized website. Maybe I don't think GitHub is the best tool here to kind of build it. Like if you want to you could put your component, that project maybe instead of like a GitHub repo in like a gigantic list somewhere where people could just search for it. So like basically a search table, I guess.
Yeah, like we've kind of gone a little bit in that direction. It's very, very hidden. Like on our side repo, we have tried to create somewhere under the list of components. There's a couple of pointers to third party, like other people that have their own side components. It's very hidden. It's very like, I think we need at the same time, like I think Z, like you're saying, like I think we mean for this to be an ecosystem. So there's going to be some heterogeneity implicit here. I don't think the solution is to centralize everything, but maybe a centralized list that kind of points to everything would be the good way to start, because there's different, with the component ecosystem, there's different licensing requirements on different components, different, so obviously we're not expecting that everything would come in one central place, but we need a way to make that all searchable. And so I like this idea of, and I don't know, like, I mean, we could host something like this in a more prominent place, maybe on the GitHub, on the side GitHub side, but I'm not sure if that's the right place. And I'm not sure if anyone has ideas about what would be a good place, where that could be hosted. I'd be curious to hear as well. Yeah. I know, Mohammed, you had your hand, and Willie, you also had your hand up. I don't know if you guys want to add something to this or.
So I just want to say two things. One is that it's good if we could, I mean, there are a lot of low-hanging fruits that essentially the applications that people would like to have. And I think if we could, I mean, that's also on my to-do list, is that if we could just create some easy-to-use kind of, let's not call them products, but softwares that people could use for their research or for development. I think that will maybe generate more visibility for and maybe add people to the community.
Right.
And I think the second point I want to mention was again, we want to have some form of a, I mean, let's call it a marketplace, even though there won't be any transaction,
sure.
As you mentioned. But then it shouldn't be. I understand that this probably cannot be done by Microsoft. Maybe it has to be somehow, let's say, should be community driven,
right?
In particular, because of all these licensing issues. So, for example, in OpenSys, we have components that they are, let's say, free to use for research, but we don't have the license to them ourselves. So, but again, we want them to be accessible to others and
right.
searchable. Yeah.
Right. That makes sense. Willie?
Yeah, so I was thinking about this sort of question over the weekend, and one thing that came up was I was wondering how much we could use the NuGet system. And so when I was working on the class project and I wanted a different speech recognizer, I didn't want to use the Microsoft speech recognizer. I wanted something a little bit more robust, but I also didn't want to start using some of the cognitive services, and I didn't want to be having to pay for every time I wanted something. So I wanted to use deep speech. Mm-hmm. And so I went looking at deep speech, and I found there's a NuGet for deep speech. So someone had already created a C# package to bridge to deep speech. And so then I created a side to wrap that and then created my own NuGet for a Psi deep speech. And I was able to do that because I was able to search for the Psi, for a NuGet for deep speech. And I tried looking to find Psi components in NuGet, and all I found is the stuff that Microsoft has published. And I haven't been able to find anything else. And one thing I found when searching for the deep speech component is that then they provided me a link to their GitHub repo and to their source code all through the NuGet page. So it seemed like maybe a useful intermediary.
Right. That makes sense. I mean, NuGets also make, like, the thing with, you mentioned NuGet packages, I think that's another, it takes more work to generate a NuGet package, but it also simplifies consumption. Like I think it's good for the community because it makes it easier on the other person sometimes to use that. Now it depends on their use case. If they're just, if they actually want to modify your code and really like go in an open source way, they need your code. But oftentimes when you just want to use a component, like NuGet is the most sort of easy, straightforward way to do it.
But even if they want to modify the code, if at the NuGet page, you can have a link to your GitHub repo.
That's right. Right. That's right. That's right. That's right.
Yeah, I agree with having something searchable. I think that would really help. My only hesitation with NuGet only is that it's a little harder to get visibility for things that you say plan to build. And I think that would be really useful here as well. If we could have a forum where people can give maybe some more kind of future plans so that other people could help them with those things before it's a finished product or at least, version 1. I think in the past we've experienced this is that we've considered wrapping something and we've maybe had discussions with people who said that would be useful, and that's a big motivator for us to wrap that specific thing versus a different, like as you say, Willie, like your choice of speech recognizer. There are umpteen different speech recognizers you could wrap, but getting a consensus amongst the community about which ones would be the most useful would be a real motivation to then like build those. So something searchable, but also that links to somewhere where people can edit and kind of the community can keep each other updated about kind of where they're going.
Yeah. That makes sense. I think that brings us also to this. Like I think this whole discoverability is a big, like I would have loved to know about Willy's deep speech or components. And so I guess even if we create, I guess the expectation might be if we create a central place where there's a list that's maintained, it would need to be a community maintained. Like when Willy does his component, he has to go there because I won't know, and kind of say this exists. So hopefully we can get to that point where people can just sort of update that page wherever that is, whether it's a wiki somewhere, whatever it is that kind of like says this is what exists and creates visibility. Because I think sometimes there's also duplication that might happen of effort in the absence of something like that. So I think that's something that's very important that I want us to kind of really kind of put our thinking hats on and make it happen, because I think it's at a point where it's starting to become really, really important. I see there were some other comments in the chat. Someone else also mentioned that since many projects, are hardware dependent, it would be useful to also document in relationship to these components, perhaps the requirements associated with them. So there's probably even like, there might be even, and I'm not sure, for instance, I haven't used myself ROS a lot. I'm not sure in that world or in other worlds where there's these ecosystems where there's almost like, I can envision almost like a kind of like a little descriptive sheet for this particular component that talks about even requirements or things like that. I think we can think through that, and probably will evolve over time into but I think that's another good point.
I would say that NuGet would solve some of the dependency problem because it handles that for you. So that like I think it actually brings up one question I have for the site team is like, so NuGet has dependencies on other NuGet. So like, is there a plan of like more frequent, like a consistent update of the NuGet package of the GitHub, I guess? Because like, let's say a change happened in the GitHub, like, is there, maybe there should be a consistent, like every month there's a push to push it up to the NuGet side.
Right. Yeah, I think this raises the whole question of our development process so far. So maybe we can talk about that a bit and what we can do there to kind of help things. And like this also relates, or in my mind, I guess there's a relationship here. One question that Daniel kind of alluded to is with respect to discoverability is this transparency about what's coming or what are people working on. Like how can we make things even more transparent, like not just discoverable, but not just this exists, but this is coming maybe. So Z, to your point, our process so far in development has been one where we kind of push to NuGets on some cadence every few months. You're right. We haven't been, so we kind of do a lot of development and we put out one of these kind of releases. And perhaps that's not the standard, like GitHub model. We are thinking about moving to a model where we do much more fine-grained updates directly in GitHub, but remains still a question of process about when is this other timeline of when NuGets get updated. If we do daily pushes into GitHub or on a maybe it's not daily, maybe it's twice a week or once a week kind of cadence of fast updates so that our contributions are more visible and transparent as opposed to arriving once every 3 months, like we just pushed the release, last weekend. Then, there is an interesting question here about on what cadence do NuGets updates, and this is more of a process kind of engineering process question that we, I think, need to think through. I'd love to hear if you guys have thoughts, like if is this a stumbling block, or what would you like to see?
I was just like, for me, the NuGet is more like if there's a bug fix, if any dependency packages are dependent on it, you have to wait for the next NuGet to have a NuGet version of it. So I think when I first wrote the ROSBAG reader, there was a bug where they had a weird dependency, and that wasn't resolved for like 6 months until the next release came out, because the fix never was in the NuGet version. So I can never have my component be in a NuGet version because the NuGet version is not fixed. So I think that's where I'm like alluding to. The NuGet is less about your development, it's more about bug fixes.
Yeah, no, but that makes total sense. I mean, if people are relying on these NuGets and for saying that this is a way for people to easily consume the bits, then we need to be on a faster cadence with our updates and bug fixes on that side as well, not just on the GitHub side. Yeah, I think that makes sense.
Yeah, so we have a bunch of questions that I think around like things we could discuss around how, what's it like to get started with Psi? Like, what was the process to kind of start with Psi for the first time? Before I get to that, though, I kind of wanted to add one more point to sort of what we're talking about now in terms of, some of these channels for communication and sharing each other's work. But I want to bring into that, like, are the channels we have enough for getting help from us and from each other? So, we've really kind of bought into everything that's in the GitHub ecosystem, right? So like using GitHub issues and trying to promote people to, GitHub issues when they have problems and make feature requests there. We're using Gitter, which is like this chat feature on GitHub. But I'm curious, like, is that enough? Are there other ways that we can kind of provide more channels for people to reach out and get help, not just from us, but from each other? And are there other models that you guys have seen from other open source projects or other projects that you've been involved with? Other things that we should be looking into doing more, like, I don't know, things on Stack Overflow or other places that people should be able to post questions and feature requests and comments and all, and stuff like that. So I'm curious.
Yeah, there's actually some posts from the audience as well about, like, should we have a forum for discussion like Slack or Discord or something like that? Like, what would be a good forum? Do you guys have experience with, like, or is there, like, and again, from the audience as well, feel free to give us ideas about what you'd like to see happen. But I'm curious to hear on the panel if anyone has thoughts on.
Well, I personally, I think that there's one type of kind of forum which is more technical, kind of devoted to discussing details of implementation and bugs and things like that. But then I think it would be great to have another type of forum for more, because a lot of people in this community are on the research side, and so talking about research projects, plans, like, and kind of thinking about those longer term things. I think that would be, and Slack might be a good place for that type of thing, where it's still very asynchronous, but we can maybe not things that are related to a specific, like, pull request or a specific even a specific component, but just broader discussions about how we can form collaborations, how we can contribute to these broader projects as well. Like, again, it's motivating when someone says they would really want this type of component. As someone who mostly works on building components in Psi, like, that's somewhere I feel like I can help, but don't always have the visibility to kind of know what would be the most useful. Yeah,
so there's a couple of upvotes on that whole Slack Discord kind of forum idea on the chat. So I think we should very seriously consider that. Now, so far, just to kind of bring everyone to the same page, our main kind of channel has been the GitHub site. And I would encourage people just in the next couple of weeks and months until we decide and figure out all these different things as we move forward, to kind of stay tuned to that, because we'll probably, like, if we decide, let's say, okay, let's open this Slack thing, we'll announce it there. And that will be kind of your way to probably hear about it and discover it. But yes, I think something like Slack sounds good for discussions of that form. In the meantime, if you have any burning issue today, or like anything that, like, not necessarily burning, but like that you want to talk, we can also use for now. But I think we should move to a better forum. But we can use. Feel free to use. I would encourage everyone to use just GitHub issues. For these things, file an issue. I'd like to encourage people. So, like, even for discoverability, we have on the GitHub site for now a who is using kind of page, and we have somewhat hidden, maybe we'll bring it to a more prominent place, kind of like list of components that we know of that exist somewhere else. We'd love to encourage everyone to kind of, if you're working on something, just like you're posting, there's quite a bit of messages in the chat about what people are working on, if you don't mind filing an issue and just say, hey, I'm working on this, just so that people know, for now, until we kind of move to the right kind of forum and format. I think that would be a good kind of just to get started, and we'll figure out a way to transfer all of this into a more kind of like organized way. Mohammed, I think you had your hand up as well. I'm not sure if I derailed the conversation
yeah,
here.
No, it's okay. No, I just wanted to mention, because we talked about Slack. I think Slack is great for kind of maybe more immediate needs, but it's good to have, maybe it's good to use something that is searchable, because people will find if things are archived, they're public. We will attract users that way, because people will find online when they're looking for certain problems. And I mean, I don't know. I mean, Slack is closed in some ways, and I don't know, if you don't have the paid version, it might not keep the archive forever. So that might.
I see. There's some
Well,
trade-offs
the
there that
conversations
we
we want to have is actually public. So I think it's good to have it somewhere that is archived. And
yeah, I mean, so the GitHub side is certainly one place. I don't know if that works, right? Like that is one place. I don't know if there's enough mechanism there for filtering and distinguishing between the different kinds of bugs, issues versus this kind of discussions. Like you can have long-running threads in an issue with the discussion. But yeah, I'm just curious.
I think the problem with GitHub, sorry again, is that I feel like that people, I mean, as Dan mentioned, some people are more like users, and those people don't dare like opening an issue, because they think, oh, maybe the problem I have is actually more of just like a random question. It's not a problem with software. It's not a bug that I want to open an issue for. So that's why it's like. And you see with some open source projects, they actually don't like it when people go ask questions in the issues. They say, oh, this is not the place to ask questions. You should go somewhere else. That's what I'm saying, is that there's no consistent, let's say, standard of but I think that if there's a mailing list, or if there's a forum, I think that be kind of, you can even have a guideline on top saying that ask this kind of questions here, that kind of questions there, and there's a Slack channel. As well. I think that at the same time, it's good. Maybe it would be a good way to grow the community, because people will be able to find answers to questions.
Yeah. I know, Z, you have your hand up. I just wanted to interject briefly in response to Mohammed. So I guess there's many kind of different cultures and how to do things, how to organize yourself in GitHub and so on. I think one thing I would like to encourage people, I think it's, I mean, in my book, I guess it's fine to kind of file issues for a number of, not necessarily just for bugs. For instance, I would encourage people, this with respect to the side project, one of the questions that's in my mind is, how do we also foster more contributions, right? Some contributions, it might be of a nature because of licensing or work or whatever, where it's not integrated in the side repo. It lives somewhere else. So like you said, we need something searchable, right? Some other contributions might be like, hey, I fixed this problem inside Studio, or I used it this way and I realized that I can accelerate this by doing this. And so, so imagine some contribution might come back in our repo, and we're welcoming. I would like to encourage more people to get involved. We really mean it to be open source in the sense of having collaborators from outside. And so, I would encourage people to file issues for things like, feature wanteds, things like that are not, or documentation needed, or even things like, I'm working on this. If anyone else is interested in it, I can, or I'm working on this and I'm hoping to put a pull request in, just to create more transparency in what everyone is doing. I feel that GitHub is one place where people could easily see it, but certainly I think we should look, like you mentioned, these trade-offs with forums, what is the right format or medium, I guess, for these different things. But I don't want to put people off of, I want to encourage people to file more issues, even if they're not just bugs. Because I don't think we're at the point yet where we're overwhelmed by, and not being able to manage it. So, yeah.
I think you might regret it when
I might regret this. This might be, this might fall in the category of famous last words, but let's see.
I was going to say there's also GitHub also have a discussion tab now, I think. You can enable that. So instead of issues, there's also a separate discussion. I think that it made it look like a forum kind of. I've only seen some Git repos have that, but it might be an option, split it up, and then it lowers the barrier a bit, saying, oh, this is discussions. It's stressful as an issue.
Right? You're always way ahead of us, Z. I didn't even know that.
Yes, we need to catch up. There was one other question I saw at some point go by, which was about, this is a bit of an aside, but I'm curious if any of you guys, are all of you guys using Psi on Windows? Someone was asking about trade-offs, if anyone has used it on Linux. I don't know if anyone on your side can speak to that.
So
Z, you have your hand up, I think, and Willie maybe, but go ahead, Z.
I use it a bit. It's tricky because of the type of components that is limited a bit, and then it works. I think it end up like it was easier for me to just have a Windows system running and then just pipe everything to Ross that was living on a different computer, which is running Linux. Then having it on. The tricky part was it doesn't work that well with Visual Studio. Is a very powerful tool. And Visual Studio, sorry, no, the Visual Studio.
Visual Studio, okay, the IDE, okay.
Yeah, the IDE. Okay. Visual Studio Code is great, but I had trouble configuring it such that it showed everything correctly, and debugging it was hard on the Visual Studio Code side. And then one of the components I want was broken, so I just went back to Windows. But that's my story and like that, but mostly work. Yeah.
Yeah, so I run on a lot of different platforms. So in the class project that I ran, I don't have control over the students' machines. And so obviously I had to run in a very heterogeneous environment. But I also had some components that were very Windows dependent. So I had some students that were running Windows. I made sure every group had at least one Windows user, but also people were running Linux, and some students, and actually probably more than half the class, 2/3 of the class was running on Mac. And so for most of the students, they were able to run portions of the system all on Mac with no problem. And for the couple of components that were really dependent on Windows, I made sure that they had some good Windows machines in those groups. And then this is where I really made heavy use of the data store. So since I can kind of isolate to which components need Windows, I can then kind of record a data store of kind of the output of that component, share that data store with another group that is not using Windows, and they can almost, in a sense, benefit from the other group's Windows usage. And so I can manage kind of this heterogeneous platforms by leveraging the data stores. And this is actually what one of my students is doing right now. When he goes back to his dorm room and wants to write some more code, he's got a Mac. And so when he comes to the lab, he records the data store, puts the data store on his Mac, and then goes back to his room. And so here in the lab, we have a Windows machine, record the data store, go back to his room. He has a Mac, and he can still continue to work.
Got it. Yeah, it does. Sorry, Sean, were you going to say something?
No, I was just saying that's interesting. That's a good, interesting setup.
Yeah, like I think stores help in a number of ways. We do a lot of development just based on stores, where we collect the data and then do a lot of development, even though it's all like we are particularly working on Windows. But I think it sounds like from both your response and Z is like part of the bottleneck here is the component ecosystem. Like I think the runtime probably works pretty fine. It's more about the fact that certain components, like perhaps media components or other kinds of sensors and so on, are not all quite there on Linux. And this brings it again to the contribution story and the fact that really, like, again, we want this to enable people. I think it's about people contributing in the end and us getting slowly to have more components in the ecosystem and then on all platforms.
Yeah, and specific to that, I mean, we do most of our development on Windows, but we try to design the components as much as possible to be agnostic. But I think it's, in a lot of cases, kind of that middle layer of components. As you say, the runtime's good, and like running a lot of machine learning models is fine, but accessing like things like voice activity detection or just like basic things that might be coming before running an ML model. I think that would be what I would say would be the priority to kind of in my mind at least, like to address.
I do remember there was an issue at some point where like stores in Linux was having trouble opening in Windows, and there was like I had a trouble at some point. I don't know, it might have been fixed, but that's something. I think that was one of the tricky points I ran into at that point. I don't know whether Willie had ran into that too.
Yeah, we did run into that, and I think it got fixed because as soon as we moved up to the newest NuGets, that it worked on the platform just fine.
Helen, I feel like maybe you wanted to jump in there. I forget. Like I got.
We actually, I don't have much experience using it on Linux. We managed to build pretty much 95% of OpenSense for Linux, but as Daniel mentioned, we had troubles exactly with voice activity detection because we rely on Windows library for doing the voice activity detection for us. So it's essentially speech recognition, which is running on Windows locally. So this was the main reason we actually couldn't port the whole system to Linux. Essentially, just this small bit over there.
Yeah. My hope is that. Oh, go ahead. Sorry.
And we're looking at other solutions for this particular problem, and then essentially it's just a matter of replacing one component, and then the whole thing is suddenly up and running. So that's why it's really nice to have. If maybe there is a Linux voice activity detector component out there that I don't know about, and it's very nice to have this centralized way of sharing all that information. So if there is one there, we can actually just take it from when somebody else developed it, and then we can have OpenSense actually running on Linux as well, which is not really the case at the moment. Yeah.
And that's why, like, I think, yeah, it all comes down to this component ecosystem and how rich it is and how fast we can get the richness, both Windows and Linux to where we want it to be. I do think there's probably, I mean, there's not a large tax to wrapping. Like if you have an existing technology, wrapping it in a side component is relatively straightforward. I don't. It's a lot of rocket science there. So it's more a matter of discovery and also understanding what the need is. So that's why I'm saying file a feature request issue if you're missing, I'm missing this component, and maybe someone else in the community, or maybe if it's not a feature request on whatever forum, we're going to move forward with, kind of finding ways to, like, I don't think it's very costly. I think some of these technologies exist, and I think at least on the processing, low-level audio visual processing side, a lot of these things today are done with deep nets and with models where you just kind of have an Onyx model or something that just runs, and SCI already supports running some of these models. So it should be pretty straightforward to populate with more components in that direction. Hopefully, I guess I worry more about hardware and sensors and things like that, where things are closer to the metal and to the OS. Perhaps, but even there, I think, yeah.
Yes, actually, we developed this component for biopack systems for measuring physiological. So it's essentially a sensor component, and this one, unfortunately, at least the only thing I'm aware of is running under Windows. So there are certain, for example, sensors and the way the operating system is actually communicating, like drivers and things like that, or some kind of a middle layer communication tool which you need to use to communicate with the hardware. Right. This might be a limiting factor as well, even though SCI itself supports multi-platform. There might be, especially on the sensor side, there might be some problems actually making it. Especially if it's like a commercial sensor, which you don't have really a lot of control over the interface.
Right. That makes sense. Another kind of class of question in my mind is, I guess it relates again to kind of contributions and getting more people engaged and getting sort of, other contribute directly to the SCI repo sometimes, like, one of the techniques I've seen in some repos is, for instance, people posting like help wanted topics, like, so this comes back to more transparency from us about what's in our backlog, what do we want to be building, just in terms of the core SCI repo, there's this other dimension of like feature requests or component requests and so on, but I'm just thinking now of our backlog and of all the things we know are in our head that we want to build them and where we could use some help. Do you think that would be a model where people, because I part of me is like, I'm a bit like, in some sense, people often get engaged because they care because they're doing something with it, right? And so then they're going to build like, like let's say, you need a voice activity detector on Linux. If that's the only thing you're missing, maybe you're going to say, well, the rest of this is so great, I'm going to take the effort to build this and contribute it. But do you think it makes sense for us to kind of become more transparent in terms of our work items and just kind of try to solicit help that way? Or are there other ways you see through which we can get more people that are just excited to engage in an open source project to try to contribute directly with us kind of in the code base? I'm curious if you guys have ideas along those lines. Mohammed, I see your arm raised.
So I think maybe it's good also think about whether we want to, I mean, who's the user base? Are we going to go beyond like HRI, multimodal interaction people, or like researchers and students? Because if we want to go beyond that, maybe it's good to think about like, can we have any connection to mobile development or web development? Because that's where probably maybe most of the developers are, because they want to develop apps or something that runs on the web. So I'm just thinking that if you want to like broaden, let's say, the community and bringing other people, that's good. The other thing I want to mention is that it's good for the users or for us. It's good if you actually say what is in development, like what comes out. I know that you say sometimes I just send email and ask, but I think it's good to know what is actually. I know that sometimes there are probably things under development that you don't know if you're going to release or not. That's also something. But if there is a plan to release something under SCI, then it's good to say this is like.
Yeah, we for sure need to do a better job on kind of transparency on our roadmap, especially since we've had this kind of cadence of pushing big releases every 3 months. So we promise we'll do better on that front for sure. But yeah, to your first point, like I do think like SCI, we started it and we view it as kind of, we started as a research effort and to support work of other researchers. At the same time, it's very like, I could see it totally used in a lot of, other systems that are not necessarily research academic kind of in nature, but they're just, processing multimodal streaming data. And so there's broader communities out there to be engaged. That's partly with this workshop we're hoping to reach a broader audience than, we initially started with the project a few years back. And I think there's IoT, there's a broad community of just thinkers, people that work with devices and try to construct interesting systems. And I think reaching out to that community would be really good. Yeah. Willie, I think you had your hand up as well.
Yeah, so I'm also interested in this help wanted sort of idea, and for 2 reasons. One is I sometimes have students come to me looking to just get more experience in projects and whatever. And a lot of times I tell them, go find an open source project, see what kind of help they're looking for, and get your feet wet. And a lot of times what I tell them to look for is not just look for kind of these help wanted postings in these open source projects, but specifically some of these projects have a get started here sort of issue. And so it's like nice, easy ones that are low lift. They're still a good contribution. It's a way to kind of get you started, especially with a large code base. So the help wanted and kind of start here with help wanted, I think are 2 good things. But if I want to take the help wanted in a different direction, so way you referenced the help wanted is Microsoft just sharing more of kind of your roadmap. But one thing I heard from Colin and Daniel is that they both ended up wanting the same thing. And so it'd be great to have a way to actually share that, hey, wow, this is something that we want. I come to find out when I wrote the SCI deep speech, what do you need? What do you know? I needed the exact same thing too. So we all ended up having to build the same thing. We all had to have the same problem of like, how do we get this run on .NET Core? And well, we can't really run on .NET Core because we need the voice activity detector. So we all ran into the same thing. And it would be great to be able to kind of use the help wanted feature for that.
Right. No, that makes sense. And I think that having those kinds of help wanted, get started, feature request, or I'm developing this feature or whatever kind of tags on the issues or some kind of place where people can easily see them, I think would be really important. Daniel, I see your hand is up as well. Oops, I think you're muted.
Sorry, yeah, just want to echo that and say, I can imagine kind of a sort of Kanban board where people can like, say, oh, this component's in progress. Like these are components wanted. I'm working on this one, like give maybe a TBD date. I've had the situation in the past where I've heard someone else is working on a component and then but maybe it actually never materialized. And so like I could have done it, but I was like waiting for someone else to do it. So like a way to kind of facilitate that, like just for it to be a bit easier to update rather than just emailing people, as you said, Mohammed, to get updates, like something that's kind of more like a bit more live.
Yeah.
And the other thing I think just want to add before we end is the creative coding communities like Open Frameworks, Cinder, these types of platforms, they do a really good job of showing end products. And I think that would also help the community a lot. Like we talk a lot about components here, but I'd love to see demos of what you're actually building, because that would motivate a lot of people, I think. So is there a way we can use that forum to get more of like these visual examples and like, you know, things like that?
I think that's absolutely right. So I think that's a great point. I really like that point. And I do think we need to create more demonstrators of what each of us are doing with these technologies and everyone else out there. And again, it's the same kind of, how do we, I don't know, where's that central place, or where do we display this, whether they're pointers from a GitHub site, but it would be nice to be able to go to one location and see these things. People are also mentioning on the chat that, you know, sometimes the problem with decentralized repositories or centralized pointer lists is that they quickly become stale, you know, and then you have a long list of things that have been dead for 2.5 years. And, you know, so it's a bit tricky, but part of me, I am almost wondering, isn't it like GitHub issues, and you can see how active it's been or something like that? Maybe that's a place, or the GitHub discussions that Z was pointing to. Maybe there's a mechanism where you can kind of get a sense of it over time. Like, is this still an active thing? Is it going on? But I love your point, Daniel, about the demos and creating more showcases. Callan, I think you also have your hand up.
Yeah, just a quick one. I thought maybe we can have a demo conference on Psy where people actually come and submit just a short description. I have this system I want to showcase, and we can all see and get the description of what kind of components are in there, what kind of problem it's solving. Just to reiterate on what Daniel just said, and I think Mohammed mentioned this at the very beginning of the discussion, that applications and showcasing is probably gonna be quite helpful.
Sounds great to me. Yep. Z?
Oh yeah, I was going to echo what everyone said. I think, again, I think bringing back to ROS World, they have ROSCon, which is like a conference where people showcase different ROS things. So I mean, a SciCon, I mean, I don't know whether that's the right word, but like, yeah, like it's cool. Maybe a way to see what other people are working on. But about contribution, I wonder whether it's like we have to, maybe at some point we'll reach the critical mass where you have everything you want except one thing, and at that point people will build that one thing. And I think we're slowly getting there. I talked to people, they were like, oh, I want to do this with nows, but I cannot finish the last part where I connect to a now. So like there was these questions like, all right, the last part, or like, but that's a very big daunting task of connecting it to a now. So like if they have everything else and then they just want, oh, we just want to do better activity monitor, action recognition, then that's where their research is, then they can focus and build a component. But I think that's one way I see these more research, at least in ROS. It turns out to be like that, like they use everything else to do everything else, and then their research is the component that end up releasing in the public.
That makes sense. Makes sense. I think that we're close to time, guys. I don't know if you have any final thoughts or.
If you want to have a SciCon, like at least on a small scale, we could organize the satellite even next to one of the conferences.
Yeah. That makes a lot of sense. Let's talk about it. I like that idea. So having some of these co-located events with some of the conferences, perhaps, and going from there. Well, I wanna, like, in the interest of time, I don't wanna run over too much, but this has been a super fun conversation. Thank you so much to you guys and to everyone else in attendance, and all the comments that have come in through the chat. We hope, like I said, that we'll be able to kind of take this to the next level and continue to evolve the ecosystem and have better processes, basically, and more transparency to kind of get more people kind of and support and nurture the open source community, get more people involved. So thanks again, everyone.
Yeah, thanks everyone. That was a great discussion.
Thank you.
Thank you.
Thank you.
Thank you.
We'll see you guys tomorrow. I think the workshop for the attendance continues tomorrow morning, I think at 9 a.m. Pacific time.
Yep, we'll see you all tomorrow.
All right.
Bye.
Bye.